Okay, can you hear me in the back? All right, great. Good morning to this Delta Independent Science Board Emerging Climate Research Symposium. Actually, in reality, this is also an ISB meeting, so I have some formalities I have to follow, so bear with me on that. First thing I have to do is to call this ISB meeting to order. So let me first talk about the public comment process. The public will have an opportunity to comment on each agenda item. We will not divide the board members, and I will recognize the board members in a few minutes, and also questions from the general audience. The in-person participant, if you have a public comment, please raise your hand. While the Zoom participants, we have equal number on the Zoom in the Zoom room. They should use their raise hand function. And it will help if you, when you ask a question, if you state your name and the organization, because that will happen, that will help the folks online. So first thing I have to do is to take the roll call for the ISB members to establish a quorum. I haven't done this before, so this is my first time. I will do, hopefully I'll do it okay. So first thing is, please, members of the ISB, please stand up. So you all know, okay. All right. Are we missing anybody? Okay. All right. Okay, there you are. Thank you. So you can sit now. The staff will move the microphone around. And this is another formality. Please, the members, please state your name, affiliation, and if you have any declarations. And I'm going to call you alphabetically. But before that, I want to recognize two new members of the board. Steve Lindley and Kathleen Jones. Can you raise your hands? Yeah. And also I want to recognize, well, we'll come back to that later. We have another board member, Peter Goodwin, who is coming starting next month. So he'll join us next month. So, Dr. Heikela.
Tanya Heikela, is it on?
Yes.
Okay, Tanya Heikela, no new declarations.
Okay. Dr. Jones?
Kathleen Jones, Independent Science Board and NASA. Can you hear me?
We cannot hear you. Is that on? Yeah. You may have to speak a little
Kathleen
louder.
Jones, Delta Independent Science Board and NASA Jet Propulsion Laboratory, no declarations.
Okay, thank you. Dr. Lindley?
Good morning, Steve Lindley, UC Santa Cruz, new Delta Independent Science Board member and formerly NOAA Fisheries.
Dr. McKnight?
Diane McKnight, University of Colorado Boulder, no new declarations.
Dr. Michela?
Anna McCulloch, Carnegie Institution for Science and Stanford University, no new declarations.
Thank you. The next is me. I have the longest name. That's why they call me Obey. Jayant Obey-Sekar, Florida International University, no new declarations. Dr. Wanger?
Hi, Lisa Wanger, University of Maryland, Center for Environmental Science, no new declarations.
Yeah. We also have two board members online. Dr. Rose?
Kenny Rose, University of Maryland, Center for Environmental Science, no new declarations.
Thank you, Kenny. Dr. Werner?
Ingrid Werner, Delta Independent Science Board, no new declarations.
All right, thank you. We also have Dr. Dale and Dr. Nyman in the audience who finished their terms end of August. Can you raise your hand at least? Where's Bob? Yeah, there. All right. So I think since there are many members of the public and those who have not been to our meetings, I think it's good to give some little background about the board. The board is comprised of 10 nationally and internationally prominent scientists with expertise to evaluate the broad range of scientific programs of the Delta, and you see all those members we just introduced. What we do, the role of ISB is basically, it was established by the Delta Reform Act of 2009, is to provide oversight of scientific research, monitoring, and assessment program that supports the adaptive management through periodic reviews. And you see those sort of our charges at the bottom of that slide. So we have this symposium on emerging climate research. So you might ask, why now? Why do we need this? And traditionally, if you work across the country in many large systems like this, traditionally we use what we call stationarity. And the idea is the past climate is an indication of the future. In this changing environment, the future conditions are non-stationary, continuously evolving, and the science is also evolving. And there have been a lot of work in this region compared to many others on this topic, but I thought the board was under the impression we need to keep up with the latest science on various stresses and hazards that I will discuss in a minute. So we have 2-day program. First day we will cover basically the current climate projections and science for the region and related uncertainties. The word uncertainties is very important because in trying to develop future conditions for planning, we need to understand the uncertainties of various projections. On day 2, we will review the current state of climate science, how that is being integrated into decision-making for analysis. So when you look at the program, it's designed to cover the science update on day 1 and getting a little bit into how it's being integrated into decision-making, but on day 2, we will dive deeper into that topic. Also want to recognize all the other ISB members who helped put together this program, Dr. Michalak and Dr. Wenger, and also the ISB staff, Edmund Yu and also Jonathan. I don't know if he's here, but anyway, I want to recognize their assistance. So we also, knowing that there has been a lot of work, we see on the right-hand side, to be more efficient, we developed sort of using AI summary of selected documents that were available to us. May not be the latest, but covered much of the work that had been done. It was submitted to ISB, and it's an overview of climate science in the Sacramento-San Joaquin Delta. And it was generated using Google's Notebook LM, and it's available if you are interested. So what are the outcomes from this symposium? First, we would try to understand or identify the science gaps and needs related to climate projections for decision support. So basically, review the current science with respect to various stresses and hazards, and not all the stresses and hazards, but maybe some primary stresses and hazards that might be important to us. You see in the middle panel, basically review and assess how management approaches currently being used align with the latest research that hopefully we are going to hear about and also summarize in that document. We also decided, do we need a new conceptual model based on this new science? And you see on the wall, there are the ones that we have collected. Jonathan and Denton did a great job assembling those. You see on the wall, the ones that that were available to us. And during your break, please walk around and write on those, so identify if there are missing gaps or missing connections, and we will decide if we need a new conceptual model after this symposium. So I'll quickly go over the agenda for today and tomorrow. After these remarks, we'll have 2 keynote presentations. What do we know? And I will introduce them in a minute. Then we'll have a small break. And then we will have what we call an emerging climate science panel. There are, 5, I think it was 5 excellent presentations by folks who we've identified as experts in various stresses and hazards. And we'll have plenty of time for discussion and with the panel and with the audience. And then we'll have a lunch break. Then we'll go into another panel, what we call State of Science to Support Long-Range Planning. And we have another series of presentations and discussion. And then there is an open forum, which is important for those who are not on the agenda to speak up and mention the type of work they might be doing that might assist us in summarizing this climate research work. Tomorrow we'll have presentation by various organizations conducting work in the Delta and how they use this climate science. And then a panel on integrating science for decision support in the Delta. Then after lunch, we'll have breakout sessions. And we haven't decided how many breakouts depending on the participation. And we may also have remote and in-person breakouts to get their input into this effort. Then tomorrow afternoon, we'll have a breakout session reports. And then at about 4:20, I hope we can finish on time so you all can get back home without getting stuck in the traffic. We'll wrap up and basically explain to you what is next for us in terms of what we produce. Before that, I think I have to ask if there is any comment from the public on the agenda.
There are none.
Okay, is there any comments from the public about items that are not in the agenda?
There are none.
Okay, thank you, Edmund. So now with that, we will move on to the formal program. Give me a second, I need to. So let me see if I can. So we have 2 excellent keynote presentations. Daniel Swain from California Institute for Water Resources. His title of his topic is Climate Change, the Delta and its Watersheds, what we know, what we don't, and what surprises might be out there. And the second presentation will be by Laurel Larson. She's at Uppsala University, but she's not new to this region. She was a former lead scientist. She'll talk about myths of the future, state of the art, and uncertainties covering climate projections to stream flow projection. Both of these are remote, and I think, well, let me perhaps, maybe I can introduce the next panel later. Should we go ahead and?
Yeah, Daniel, you're online. You should be able to screen share your screen.
Great. Well, hello, everybody, and thank you for the invitation to speak at this. Yes, so sorry. I just wanted to make sure that you're hearing me as expected here.
Yeah.
Thanks for the invitation. And I think this is very timely, given a lot of the conversations that have emerged, both on the policy side and also on the climate science side. There are actually some relatively recent developments, so I'll try to stick around for that panel later in the day, because there are some things that are a little bit different than the conversation as it was 5, 10, 15 years ago. That's expected in science. The conversation is ever evolving. But I wanted to touch on some of those points, perhaps in summary, in this roughly 30-minute presentation right now. So let me share my screen. You're going to briefly see the infinite mirror screen share as I go into PowerPoint. All right. Unless somebody tells me otherwise, I will assume you're seeing this full screen, and I will get going. So I did want to structure this around what we know and also what we don't know, because I think sometimes we focus a lot on uncertainties in the challenges that poses for adaptation and management and making plans for the future. But I also think that sometimes we focus a little too much on the uncertainties and sort of miss the forest for the trees, in the sense that we really do know a lot about how things are changing, how they will change. And although there are large, perhaps even larger uncertainties regarding the future than we might have thought, at least in some specific respects, some years ago, I think the things that we've also learned in the recent past actually allow us to better distinguish between the pieces of our changing climate that we do have confidence in versus those that we don't. So I think the silver lining here, just to give the very brief summary of what I want to offer today, is that I do think we have a lot of information already about the kinds of changes that we need to be preparing for actively, partly because some of those changes have already begun to emerge. And just to remind everybody, since it always bears repeating, and this map of how much the Earth has warmed is now updated through the most recent calendar year, so 2024. And you notice that there's a lot of orange and red on the map. The Earth is warmer than it used to be. It's not warming uniformly in a spatial sense everywhere. There's more warming over the continents than the oceans, and there's more warming in the Arctic versus essentially everywhere else. And the main reason, of course, for this warming is the accumulation of heat-trapping gases in the atmosphere, known as greenhouse gases, that are primarily there because of combustion of fossil fuels, and then also other human activities, including agriculture, over the past couple of centuries. The amount of warming we've experienced cumulatively to date since the pre-industrial era, at least when measured on a multi-year basis, so sort of an apples to apples comparison with IPCC reports and climate targets and things like that, we're around 1.3 or 1.4 degrees centigrade of warming as of the last couple of years. Although, as many folks have pointed out, the last 2 years specifically, so 2023 and 2024, and at least parts of this year, have been at least temporarily above that 1.5 degrees centigrade of global warming. So we have seen a recent bump up in the amount and rate of warming around the world. And according to our current policy, or our current policy plans, both as implemented and as claimed to be implemented, we're still on a path toward around mid 2 point something degree Celsius warming by the end of the century. So between about 2.5 and 3 degrees centigrade. That's, of course, very uncertain and subject both to geophysical uncertainties, so climate science uncertainties, but the big one is human activity uncertainties. What do we do? What do our future climate emission trajectory, or carbon emission trajectories look like? We don't know yet, and I think already we're seeing that our trajectory in terms of our emissions today is perhaps different than a lot of folks might have predicted back in the era of, for example, the Paris Climate Agreement. So there is still uncertainty, but it's quite plausible at this current juncture that we will essentially double the amount of warming that we've observed so far, and the impacts from that further doubling of the warming we've experienced so far will likely be much greater than the impacts from the first half of that increment, because, as I'll describe here, there are parts of the climate system itself that are nonlinear, but perhaps more to the point, human systems and ecosystems respond nonlinearly to the warming that we've seen and that we're likely to see. So California, as much as the rest of the world, of course, is a warmer place than it used to be. There's been a particularly strong warming trend since the late 1970s or early 1980s in California. We are seeing so far warming that is much faster inland and also at higher elevations as opposed to the coast. The coast is warming too, but it hasn't warmed as fast, particularly in summer. And this post-2010 era, this period we've seen all this record-breaking and extreme drought and the worst wildfires on record in modern California history, have occurred during this period essentially of a sudden step up or sustained plateau of sustained warmth, where we entered this moment of elevated temperatures right around just before prior to 20 or right around 2010. And we haven't really dropped back down to where we were before. So we sort of stair-stepped upward, and we probably are not headed back to where we were before that point. Specifically, and I think this is relevant given that this summer was not among California's top 3 hottest summers, but that all 3 of California's hottest summers on record have nonetheless occurred in the past 10 years, which is not something you would expect to see in anything but a rapidly warming period. So what I really want to talk about here today is largely with respect to California's hydroclimate. And this may look like a complicated figure, but so I don't want folks to focus on the details. But the main piece here I want folks to think about, and I'll talk about this more in the next 10 minutes, is that when it comes to the hydroclimate, precipitation, evaporation, and everything that's involved in both of those fundamental processes, there is an inherent exponential equation that describes how the atmosphere changes in response to warming. This is actually known as the Clausius-Clapeyron relation. It's science that has been understood in its basic form now for the better part of 2 centuries, so longer than we've had climate models or indeed even computers around to check these assumptions. But the basic idea is that the water vapor holding capacity of air, or the saturation vapor pressure in technical terms, increases exponentially with a linear increase in temperature. So we are seeing an approximately linear increase in temperature itself with warming, yet this is a fundamental process in the atmosphere that greatly affects California's climate, both with respect to wet and dry extremes, that is, even in theory, scaling exponentially. So global warming then brings about this nonlinear increase in the thermodynamic activity or the thermodynamic processes in the atmosphere. So warmer air equals essentially a thirstier atmosphere overall. And this is something that's present not only in theory, but also in climate models. So we see this in the predictive models that we use for the future, which is good because we know it's true based on instrumentation and observations. And we also see that in real world observations. So this is a pretty fundamental concept that we see is in alignment with theory, model predictions, and observations in its most fundamental form. That all sounds a little bit complicated, so my colleagues and I have recently coined, an analogy which maybe helps visualize this, which is that of the expanding atmospheric sponge. So imagine that the atmosphere at any given point in time, at any given temperature, acts like a sponge with some capacity to absorb water. Think of it as an ordinary kitchen sponge. And then imagine then that with warming, that kitchen sponge becomes exponentially larger. With 3 degrees centigrade or about 5 degrees Fahrenheit of warming, that's about a 22-23% increase in the size of the sponge. So pretty substantial. What this means in practice is that as temperatures rise, the ambient air becomes, if you will, spongier, meaning that it has an increased capacity to absorb water if there's water available to absorb, and also increased capacity to yield water if you figuratively wring out that atmospheric sponge when it's saturated. So that means, in practical terms, it raises the ceiling both on how intense precipitation can become when conditions are favorable for rain or snow, but also on how intense evaporation can become most of the rest of the time. So you see an accentuation of both precipitation extremes and evaporation, or at least potential evaporation extremes, limited only by there being water available to evaporate in the first place. So in practical terms, heavier downpours, but also greater atmospheric thirst. Net effect being something we term increasing hydroclimate whiplash. So taking a quick step back here, and just thinking about why California has what you could call an inherently whiplashy hydroclimate to begin with, is that the state exists at a climatological transition zone between the more stable, quieter weather-wise subtropics and the much more active mid-latitude temperate climate to the north. That's partly because California exists at the margin of really where the jet stream, that river of high velocity air in the upper atmosphere that defines the storm track, that jet stream shifts seasonally, which you can see on the illustrated on the left here by the extreme seasonality of California precipitation, where much of the coastal region sees no rain at all, essentially, in summer, and then has this gradual increase from fall into winter when it peaks and then attenuates as you go back from spring to summer. That seasonal cycle is largely because the jet stream itself has a similar cycle of strengthening as you go from fall to winter, weakening as you go from spring to summer, and also shifting latitudinally northward in summer when the more subtropical stable regime dominates in California, and then shifting southward in winter when that more unstable mid-latitude regime tends to prevail. This isn't something that is perfectly fixed in time or space. In fact, one of the reasons why California is so susceptible to drought is that we have a singular wet season in the winter. We don't really get a lot of rain in the summer. So if we don't get that rain and snow in the winter, we're kind of out of luck, at least until the next winter season. And the jet stream itself does very different things from year to year. So not only do we see strongly seasonal cycle of California precipitation, but we also see a lot of year-to-year variability because in some years the jet stream is stronger and shifted farther south than in other years. So we have that jet stream wiggling around latitudinally and bringing us very different water years, some of which can be extremely wet when it's centered farther south for more of the season, or very dry when the reverse is true. And that is one of the main reasons why we have this highest coefficient of interannual variation of precipitation anywhere in the continental US. And I think really if this map on the right from Mike Dedinger's paper about, I guess that's over a decade ago now, were extended to all of North America, this would actually be pretty unique even within the rest of North America as well. So California really does have a more variable hydroclimate than certainly most places in the United States, but arguably than most places even in the world. So what's going on recently in California? Well, notably, there's not a huge trend in the average annual precipitation on a statewide basis. And yet there is a detectable increase in the statewide moisture variability. There's a few ways to show this, but for now, just think of this as hydroclimate whiplash. There's also a very strong trend towards increasing drought frequency and severity. And I just want to remind folks, this is occurring in an environment where there has not been a similarly robust or sustained decrease in precipitation. So I'll come back to that in a moment. But just to illustrate what this looks like, and this is all from Butte County, where there's a lot of critical California water infrastructure, and of course, the rivers in Butte County are watersheds to the San Francisco Bay Delta region, as we've gone back and forth with pretty wild flailing from dry to extreme wet to extreme dry to extreme wet. And really, I could add potentially even another panel after 2003 here. And I actually have similar slides from many of California's most important counties from a water resources perspective. So this is hardly limited to Butte County. And it is an illustration of the kind of variability that we're talking about here. In terms of extreme swings between wet and dry and all the consequences that come with that. There's quite a bit of research on the climate science side of things at this point that suggests that the average precipitation in California is maybe not the most important metric to be considering in a warming climate, partly because we don't know exactly what it's going to do. We don't actually have a good handle on whether California's average precipitation will increase or decrease. And indeed, thus far, it really hasn't done either in a robust way. And yet those very same climate models that predict small and or uncertain changes in California's average precipitation show a large increase in the wettest wets and a slightly lesser increase in the driest dries when it comes to precipitation alone. Now, when we add in evaporation, this becomes even a bit more dramatic. I'll talk about that in a moment. But the gist of this is that we expect to see, even in a world where the average precipitation in this part of the country could increase a bit or it could decrease a bit, we don't really know, that the tails, the distribution on both ends, will likely be broader. And that leads to an increase in the interannual variability of precipitation beyond even the already high levels that we see now, what we call increasing precipitation whiplash. This is perhaps even true on a seasonal scale, where we already have a strongly seasonal cycle of precipitation that peaks in winter and is at a minimum in summer, as I mentioned. This sets the tone agriculturally, ecologically, and even in terms of the daily rhythm of life in California. We have wet winters and dry summers and some transition seasons in between, but there is some evidence that those transition seasons may become a bit drier and that the winter may become a bit wetter on average. So a further accentuation of our already fairly dramatic seasonal cycle. That has pretty significant implications for agriculture, as it would increase the length of both the growing season, but also the needed irrigation season. It has huge implications for things like wildfire risk and the health of ecosystems, in particular in autumn, which is peak flammability season, of course, in California after our long dry summers. And critical from a water supply perspective, it also has big implications for snowpack, in particular on the Sierra watersheds, because you have a later start to the snow accumulation season, an earlier end to that snow accumulation season, and also potentially more intense runoff during the time of year when we are getting that precipitation. This, by the way, is not necessarily a reflection of temperature. Rising temperatures, of course, will further shift our snowpack, but this is just a reflection of the seasonal shift in the actual arrival and departure of precipitation itself, amplifying those changes in snowpack that we like to see, that we expect to see from temperatures. And so, as I mentioned, we don't really know what's going to happen with California's average precipitation, but there's pretty high confidence that the variability, both within seasons, so even week to week, month to month within winter, and then from season to season, will probably increase, even as we can't really give with high confidence a statement about what might happen on average. When it comes to the extreme wet, of course, in California, typically this means wintertime storms, and by wintertime storms, the wettest ones are usually atmospheric rivers, these narrow corridors of highly concentrated atmospheric water vapor that can flux enormous amounts of water, akin to many times that of the flow rate of the largest rivers on Earth, like the Mississippi River or the Amazon, into California in the form of water vapor moving quickly, pushed by winds in the air above your head. And when those atmospheric rivers, when those plumes of extremely concentrated moisture hit California's coastal mountains or the Sierra Nevada, that air is raised by the effect of intersecting with the topography and often falls as very heavy precipitation. This is a key piece of California's water supply, but also the primary cause of California's major flood events. And we expect these events, especially the most intense ones, to become considerably more intense in a warming climate because of that expanding atmospheric sponge effect that will eventually lead to the occurrence of atmospheric rivers of unprecedented strength. Again, we don't necessarily know whether we'll see more atmospheric rivers overall or not, but we are saying specifically that the most extreme ones will likely become more so. There's a long history of atmospheric rivers causing some problems. From a flood perspective in California, we may be familiar with the Great Flood of 1862, a flood that of a magnitude of which we haven't seen on a statewide basis since the advent of modern water infrastructure in California, but the paleoclimate record suggests they happen every century or so. So they're unusual in a recent context, but far from rare in an Earth history or geological context. A modern day repeat, suffice it to say, for today's quick talk would be pretty disastrous for modern California. And we expect that there's a considerable increase in risk with a warming climate. In fact, we looked at this pretty directly in a study in 2022 as part of the ArcStorm 2.0 project. And what we found is that the risk of a very large flood event, potentially even of a magnitude of an 1862-like flood, has probably increased significantly already, perhaps doubling, in the background in a period where we've actually experienced a lot more extreme droughts than we have severe floods. That appears to be because, and some research from other groups recently has backed this up, is that natural climate variability has kind of overridden the human-caused warming signal in terms of its effect on flood risk in California over the past couple of decades, meaning that natural variability has essentially masked the background increase in the risk of a big flood event. That probably won't continue forever, which means that so far and recently perhaps we've gotten a bit lucky with this. So these days I'll take any luck we can get, but I think we need to be thinking about the broader context of why we haven't seen more large flood events in the last few decades. Because our recent research suggests that an 1862 level event is potentially more likely than not over the next 40 years or so, which is partly a reflection of what the cumulative risk of relatively unusual events is over any 40-year period, plus the effect of climate change. And when we did this experiment, what we found was that, well, the numbers are pretty overwhelming, literally, that we had to change the scale on some of these kinds of figures. But I just wanted to, for the purposes of today, reflect that the big floods, the big regional floods anyway, not extreme, but they were big, and they weren't statewide, but they were substantial regional floods, the winter of 2022 to 2023. If we compare the cumulative statewide precipitation to our two different ArcStorm scenarios, the lesser historical one and the more extreme future one, we got 80% of the way there in December, January, except we did so over a longer period of time, so the rainfall was more distributed. But we only got about halfway to what we would have seen in the greater Arc future scenario, meaning that imagine if there had been twice as much rainfall and it had been considerably warmer during January through December, or December through January, 2022 and 2023, and those are the kinds of extreme flood scenarios we're potentially thinking about here. So beyond precipitation itself, there's the question of rain versus snow, of course, and we know that there will likely be a dramatic shift toward more rain rather than snow, and that has major implications for runoff, particularly in the Central Valley and in the watersheds that are most proximally important for the Delta, because runoff increases very strongly in the San Joaquin Basin in particular, potentially by as much, in the most extreme storms, 200 to 400% in peak runoff increase. So these are not incremental changes. This is effectively during the most extreme runoff events with a couple of degrees of warming, potentially a novel regime. And all of that is ultimately flowing into the Bay Delta. The droughts, of course, we've already seen that they've gotten worse, primarily due to the dry side of the expanding atmospheric sponge, because the same amount of rain snow just doesn't go as far as it used to. I've talked about a lot of this, so I'm going to go through it rather quickly to not spend too much time on it, but this leads to an interesting scenario where we do expect the most extreme precipitation events to increase considerably in a warming climate. That signal historically remains a little bit elusive, but we do expect it to emerge eventually. And what it might mean in terms of flooding is that we actually have decreases in runoff for weak to moderate flood events, which might lead us to a false sense of security about the most extreme flood events, which we actually think might still be increasing at a greater rate than the average extreme precipitation because of that double whammy effect of warming temperatures and the snow to rain conversion, as well as more extreme precipitation to begin with. So consider the 5 and 10 year recurrence intervals at your peril, because it's really the 50, 100, or 200 year recurrence interval floods that cause the most problems. And those might be doing something very different than the kinds of floods we observe more frequently. And I'll just briefly touch on wildfire because it's not so important in the Delta itself, but very important for Delta watersheds in the Sierra Nevada and the Coast Ranges. But we know that increasing aridity means greater flammability of vegetation, more fire, more intense fire on the landscape, and that is already reflected in shifts towards much drier and much more active fire conditions overall. And regardless of future climate trajectory, there is going to be some further warming, and this is something that's probably going to get considerably worse before it gets better. So we really do need to engage in short-term adaptation and interventions over the next few decades to get ahead of what has become a pretty significant crisis in California for a variety of reasons. And I think the main implications from a Delta perspective are, again, what's going on in the headwater regions. Changes in runoff patterns post-fire regimes can result in stronger runoff for a number of years, and also in water quality, because of course in those regions you're going to get initially ash and debris potentially into reservoirs, which can be a problem for dam turbines and things like that. But even downstream of that, you have increased turbidity, you have sediment, you have ash that might be in the water that wouldn't have been there otherwise. So one big uncertainty, and if I'm running long, please let me know. I'm not quite sure what the timing is here, and I can wrap up. But one of the big uncertainties that I did want to raise is that, as I mentioned, we don't really know what's going to happen with California's average precipitation. This mainly comes from the fact that, well, we know the expanding atmospheric sponge raises the potential on the wettest wets, but the driest dries, precipitation-wise in California, are largely dictated by what's known as atmospheric circulation, essentially changes in atmospheric wind patterns over the North Pacific. And we don't know exactly how those are going to evolve. Part of the reason for this is that until somewhat recently, climate models generally suggested, and excuse me, I actually have a typo here. This says most climate models say a La Nina-like trend with climate change in the Pacific. That should actually read, most climate models have suggested an El Nino-like trend in the tropical Pacific with climate change, meaning greater warming in the eastern tropical Pacific than the west. So it kind of looks like El Nino in the average change. But in the real world, and this bullet is correct, no, I have these reversed, excuse me. So let me just rephrase this for clarity. Climate models have long said that there would be an El Nino-like trend in the tropical Pacific, but what we've actually seen through 2025 is that there's been a La Nina-like trend. So essentially the point is we've seen the opposite trend of what climate models predicted. And there's been a lot of research looking into why that might be, what the implications might be, what's driving this. Are we just unlucky? Are we in a particularly, for lack of a better term, weird iteration of internal variability? Or is this something that climate models are actually wrong about? It would be pretty consequential if they were. Well, making this even more complicated is a recent discovery. This was literally published this summer. It was a pretty high-profile paper that what was previously thought to be a natural trend, a non-human caused trend in the Pacific decadal oscillation, another mode of multi-decadal variability in the Pacific Ocean that affects California precipitation and climate quite substantially, is in fact actually at least partly caused by, you guessed it, greenhouse gas emissions and also other pollutant emission trends like aerosols from South and East Asia, meaning that the unexpected La Nina-like trend, which is also related to this trend towards an increasingly negative flavor, if you will, of the Pacific decadal oscillation, might itself be a reflection of climate change. And the climate models did not necessarily represent that correctly. So this is a huge amount of very complex science compressed into a very short period of time. But from a practical perspective, I think the important thing to take from this is that there are major uncertainties already with respect to how El Nino and La Nina and the Pacific decadal oscillation might change that have pretty substantial implications for California precipitation. And one key implication is that future drought risk, which has already been, of course, a major concern, if this ends up being true, and further science will elucidate more in the coming years, it might mean the future drought risk has actually been underestimated. Now, a lot of folks have kind of quietly been freaking out about this, and from a climate adaptation perspective, does this throw a wrench into our planning? And I actually don't think that it does if we keep our focus primarily on the wet and the dry extremes, rather than trying to divine exactly what's going to happen with California's average precipitation, because we honestly don't know. In fact, we may know even less about the average than we used to think we did. But in fact, the fundamental driver of that expanding atmospheric sponge is still going to dictate what happens with the very wettest wets and the very driest dries, and I think we can plan to prepare accordingly. And I have one slide on sea level rise before I start to wrap things up. Sea level rise, there is now quite good, despite recent newspaper headlines, quite good observational evidence that sea level rise has accelerated. So it's another nonlinear process in a warming world, and that the rate has approximately doubled in the past 30 years. Though to be clear, this was predicted. This is not an unexpected acceleration, but this is largely in line with predictions, maybe a little bit faster than predicted, but to a reasonable degree of approximation, this was essentially what had been long predicted. Interestingly, in the San Francisco Bay Delta, if you look at where the actual sea level rise is mainly arising from that we've seen or expect to see later this century, more than half of it directly comes from the melting of continental ice sheets in Antarctica and Greenland, as well as mountain glaciers. It's not necessarily meltwater from the glaciers, but it is the net effect of all the things that are changing, including, believe it or not, gravity on Earth, because you're shifting a lot of that really massive ice sheet water to the oceans. So you're changing the distribution of mass on Earth measurably. Always a fascinating topic. But my point is that a lot of the sea level rise that's going to occur locally in the Delta is actually the product of remote processes occurring in completely different parts of the world, and in particular, the cryosphere, the frozen parts of the world. And that remains, along with how certain deep ocean currents will change, which is also consequential for sea level rise, the topic of considerable scientific uncertainty. And we still can't rule out more extreme sea level rise than reasonable mean estimates might suggest. And I think this is a real challenge. This may be even one of the larger challenges in climate adaptation in the Delta, which is that there remains a considerably non-zero chance that sea level rise in the next 30 to 50 to 70 years, depending on the relevant time horizon for planning, could end up above the high end of the reasonable median estimates that we're seeing right now. And it is very difficult to put numbers on this currently because we don't know that much about exactly the ice sheet dynamics that are relevant for the Delta. Even though we're thousands of miles from those ice sheets, might feel like it's a distant memory. This is a classic case where what happens in the Arctic and Antarctic doesn't stay in the Arctic and Antarctic. And I think that the most dramatic example of that might well be with respect to sea level rise in places like California. And in the Delta, of course, all of this has great practical relevance for thinking about flood risk, because higher sea levels raise the pressure on levees, mean that it takes a less extreme storm to result in freshwater flooding. But even at baseline, we have issues with saltwater intrusion for the water supply, for ecosystems, and just for the permanent infrastructure that we're thinking about potentially installing in this part of the state, and all the practical decisions that are involved with deciding what standards to build that, where it should be built, or whether it should be built at all. So to sum it all up, what do we expect? Well, we expect increased precipitation intensity as well as overall aridity, a pretty dramatic loss of mountain snowpack, a contract of the snow season with more extreme heat and faster runoff. Think increased variability, increased whiplash as the clearest specific signature. The driest dries will be still drier than even what we've seen so far, but the very wettest periods, and we haven't quite seen this as much yet, will likely not only still occur to be as wet as they ever have been, but probably be even wetter. And I think that's a blessing and a curse, depending on the context, because it does mean that we will still get water. It's just going to come potentially in increasingly large and inconvenient bursts, which in some respects is better than not getting that water at all, because we will still have water to work with, but we're going to have to learn to manage it arriving in increasingly inconvenient ways, let's say. And so all of this points to the need for flexible and proactive interventions and adaptations commensurate with these physical realities. And that can mean things like nature-based solutions, but also high-tech interventions. So we're thinking about restoring floodplains, but also things like floodmar, aquifer recharge, and forecast-informed reservoir operations that help us sort of manage this whiplash, this variability. It means improving public and agency awareness of the risks and interventions through scenario building and response exercises. Stress testing that does actually stress test, that goes through the full range of extremes that might be plausible, thinking about what are the real needs in the system and what are the weak points. And I think my real message here is, despite all of the kind of maybe scary things I'm talking about today and all of the uncertainties I've pointed out, I don't think any of this is a reason that we should succumb to decision paralysis, because we actually do have a lot of information about where we're headed. We know that sea level rise is occurring. We know that we're going to see worse droughts and probably larger floods. And those statements alone should probably give us enough information to be preparing in the right direction. And then in all of this, I think that there are going to be win-win interventions that could exist, even absent climate change. And this is a moment where, at least in some circles, it's become more difficult again to talk about climate change as such, that are beneficial for people and communities and ecosystems, even absent climate change. There really are some of those interventions out there that would be just so broadly beneficial that climate change is only one of many motivators to pursue them. So with that, I'll wrap it up, and thank you all for the invitation to speak today.
Thank you, Daniel. A lot to digest there. I think we have a few minutes for questions from the audience before we get into the next keynote. Cannot believe. Okay, I think.
Hi, Daniel. This is Anna Mikulek. Thank you so much for the great presentation. I wondered if you could elaborate a little bit on the point you made about the causes of sea level rise, specifically in the San Francisco Bay Delta region. I think you quoted this 60% of the sea level rise being attributable to ice sheet and glacier melt. To what extent does that percentage vary depending on where you are in the world? You would think at a macro scale, of course, those ice sheets melting would impact sea level rise everywhere. But the way you talked about it implied that there is local variability as to how one attributes sea level rise as a function of location. And I'm wondering if you could talk about that a little bit more.
Yeah, that's an excellent question. And this is actually really fascinating because you can think of especially the Antarctic, because Antarctica is essentially one gigantic high elevation glacier. It's a continent of ice, miles thick. That's a lot of mass stored in that frozen water. And as it starts to melt, you have a redistribution of that mass from being concentrated, for example, around the South Pole to then being more evenly distributed around the world, throughout the world's oceans. The oceans, they're not rising exactly. And this is another point. The oceans are not rising evenly. The actual amount of sea level rise is different from place to place, partly because you're redistributing the mass distribution on the Earth's surface by melting ice sheets. And there currently are more ice sheets in the southern hemisphere than the northern hemisphere. So you're net redistributing the Earth's mass more toward the northern hemisphere in a way that changes the effect of gravity, literally. And so you actually have, so sea level rise overall, just to quickly summarize, is generally the combination of essentially thermal expansion of water, because the water itself is warmer. That kind of makes sense, right? But in a lot of cases, that's only about between a quarter and half of the total amount of sea level rise in any given place. The rest is generally coming from the effect of melting ice sheets. But the effect of those melting ice sheets isn't just the actual water that was formerly frozen entering the oceans and increasing the level of the oceans. It's also the redistribution of mass on Earth that shifts mean sea level in different places quite differently depending on where you are on Earth. And so because we're in the northern hemisphere and most of the ice currently is in the southern hemisphere, that can potentially actually have a pretty large effect on the northern hemisphere. And there's other pieces of complications that relate to ocean circulation as well. That number does vary from place to place. It also varies over time. So now the effect of thermal expansion is greater than ice sheets, but shortly, in the next decade or two, that will flip as the ice sheet contribution becomes larger. And that's because both of the actual amount of water melting is increasing and because the redistribution of mass on Earth is proportionally greater. So it's actually fascinating and a little bit counterintuitive that some places on Earth will actually see a net decrease in sea level specifically from the melting of the Antarctic ice sheets, because of the net gravitational effect is overwhelming the other effects in those specific locations. The thermal effect is increasing everywhere, as you'd expect, but the ice sheet effect is actually really dynamic and complicated.
I think, do you have, and then maybe, are there any questions online?
We have one online, but for sake of time, Daniel, can you, it's a Q&A. Can you type the response and we'll send it out to the group, your response?
So my question is, it would be helpful if you would expand on those win-win situations that you mentioned at the end of your talk.
Yeah, and I think I did blow through the last couple of slides pretty quickly, so that's understandable that I didn't focus more on them, I guess. I think some of these include some of those specific, both nature-based and sort of high-tech interventions that I mentioned. So thinking about why might we engage in flood-mar, for example. So coupling flood, sort of opportunistic use of flood flows to do groundwater recharge. Well, of course, in the moment of a flood, now there's two benefits you're potentially achieving. You're potentially achieving flood risk reduction by shaving a bit off the peak of the flow from the flood. Then you're also achieving the benefit of groundwater recharge, which is actually increasing resilience to some future drought. So, you may not be worried about water scarcity in a flood, but you need to be thinking about both flood and water scarcity in the same moment. So flood-mar, for example, is something that reduces both flood and drought risk potentially simultaneously. And depending on how you do it, depending on whether this is you also concurrently engage in things like floodplain restoration. That's also a major environmental and ecosystem win as well. And so here you have something that could potentially be useful, even if there were no change in flood or drought risk. We've already seen plenty of extreme droughts in contemporary history in California, and there's a long history going centuries back, especially of major floods. That already would justify a system that is even more capable of dealing with more extreme droughts and floods, even if there were no long-term trend, simply because we know that what we've seen in the 20th and early 21st century is not the full range of what could have been experienced, even before there was any climate change. So there's a reason why this would be beneficial for people, for ecosystems, and even in the absence of climate change. And that's true also of, informed reservoir operations. So leveraging our increasingly accurate weather predictions that we have to more effectively say, no, we don't need to dump that water right now from the dam. We can save it in case we need it for the drought, or saying, actually, no, there is a really big storm coming. It would be dangerous to hold it. We need to start releasing that water now. It allows us to use reoperate existing infrastructure without huge capital investments, certainly not on the scale of building new levees and new reservoirs and new dams, at least, in a way that allows us to have more resilience to either larger floods and droughts, or even better resilience to the kinds that we're already used to. We have more efficient use of water, better risk reduction wrapped into one. And again, that benefits people and the environment as well.
Move on, Edmund. Yeah, let's have the thank you, Daniel. Appreciate it. Now there's a.
Thank you. I'll answer the question.
Keep all those things in mind over the rest of the day and tomorrow in our discussion. So now we have Dr. Laura Larson. She's going to talk about myths of the future, state of the art, and uncertainties in converting climate projections into stream flow projections. Go ahead, Laura.
Hi, it's nice to see you all. Good morning. Let me go ahead and just start my slideshow here. And I trust that you can see it now. I don't hear anyone telling me otherwise. Well, it's both great and intimidating / humbling to go after Daniel Swain. I think he sets up this talk very nicely. What I'll be talking about today is how we then go from these climate projections to stream flow projections for water resource planning purposes. So that's how I'm focusing my talk here. And what I'll be presenting to you is a synthesis of the literature rather than original research that was motivated by several projects I have right now, both in California and elsewhere. So the motivating questions that I'll be dealing with are, how will climate change induced stream flow differ from the past? And as you can see from this figure here, we do know from the paleoecological record that, or the paleo streamflow record, that streamflow in California was quite variable in the past, but our models are also forecasting much higher variability in the future as well. How robust will water resource systems be to those changes is another key question. And then how does our incorporation of climate change information in water resource planning, as done by current conventions in the Sacramento-San Joaquin Basin, compared to elsewhere? What is the state of the art? So the questions that I'll be focusing on today really invoke four main research communities. Clearly, the climate science community. It also invokes communities of researchers who are doing climate impact assessments or going from the climate science to impacts on economic, ecological, and water resource sectors. Water resources planning is closely tied to these climate impact assessments. But then also I'll be bringing in my home discipline, which is hydrologic modeling and forecasting. So for those of us who are not climate scientists, I know I started out this way. I think a lot of us have this gold standard in mind that comes from reading about and learning about the IPCC and their work. And that gold standard is we use the most up-to-date climate models and feed those into hydrologic models in this case, which could then be fed into water systems models like CalSim in order to ultimately develop projections of water deliveries into the future. All of these models occur on different spatial scales. It gets a little more complicated than this, though, when we really consider the fact that there are multiple emission scenarios that are powering these global climate models. Each climate model family has a number of different realizations that are initialized through different initial conditions, but really represent the background variability present in the climate system. And then, as Daniel talked about, our system has the sea level as a boundary, and so we actually need to consider sea level models and hydrodynamic models as well. Not going to be talking about those things today, but what I hope you take away from this diagram is that there are uncertainties that are present in each of these steps in the modeling chain. These uncertainties are epistemological and stochastic. Emissions are highly uncertain. We also have incomplete understanding of physical processes like the Pacific Decadal and El Nino Southern Oscillation that Daniel talked about. And so we represent these processes in a simplified way in our models. There are also stochastic uncertainties due to the inherent randomness within the system. Of course, there's uncertainties associated with what downscaling approach is selected, how models are parameterized, even whether those parameters remain stationary over time or are allowed to vary over time, as well as uncertainties in how we reconcile these different spatial scales of modeling inputs. So the consequence of this is that these uncertainties do magnify as you proceed down the chain of models. And in fact, if you look at projected future stream flows, and this is for the Sacramento River at Bend Bridge in a paper by Jonathan Herman at UC Davis. But if you look at projected stream flows at a number of different time scales, you'll see that there's much more variability within these projected stream flows than there is in temperature. And this is even without considering some of those uncertainties that I mentioned in the previous slide, such as internal variability, downscaling, or choices associated with the hydrologic models that are being used. So there are a limited number of studies that have tried to partition the total uncertainty in stream flow due to uncertainty in these different potential causes. However, this modeling is computationally expensive. GCMs are expensive to run. The hydrologic models and the parameterization of those models also takes a fair bit of time. So this hasn't been done exhaustively in many different catchments. But where it has been done, there's a general consensus that most of the uncertainty is primarily attributable to uncertainty in climate. In fact, which of the GCM modeling families are selected to power this modeling chain? Second is uncertainty in the initial conditions or the internal variability associated with these climate model runs. And then you get into lesser sources of uncertainty, including greenhouse gas emission scenarios. And in this particular study that I'm highlighting, the hydrological model choice and parameterization of that hydrological model are among the sources of uncertainty least important in contributing to overall uncertainty in stream flow. You see some variability in different studies in the literature. But I actually would argue that more studies are needed because we do know that different types of catchments exhibit very different typologies of response in terms of how they process climate information. So how do we deal with this uncertainty? Well, there are different conventions within these different disciplines that I'm highlighting. And the state of the art within the climate science community is to really estimate that uncertainty, to get a handle on it through multi-ensemble modeling with complex physical models. And so this is just a screenshot of a figure that's in the water chapter of the IPCC 6 assessment that shows variability in projected stream flows from different basins around the world relative to the current condition. And you can see there's a lot of variability in here, but what this comes from is from running multiple climate models, multiple emission scenarios, but also an impressive array of hydrologic models that come from the intersectoral impacts model intercomparison project and the Jules Land Ecosystems and Hydrology model. Still, this type of information that you're seeing presented by the ICCC is of limited utility when it comes to individual basins that need to decide how to manage their water resources, like the Sacramento-San Joaquin Basin. And this is because of several things. First of all, there are well-known biases in the GCMs for specific regions. To some extent, those biases can be alleviated through downscaling procedures, but those are also associated with uncertainties. And when we finally get to the hydrologic modeling, the streamflow modeling, we find, at least in California, that many of the spatial correlations between different basins that feed into the Sacramento-San Joaquin are not captured in the model hindcasts. And those models also don't do a great job at reproducing spatial or temporal streamflow statistics. And in fact, one of the issues with these global climate models is that they are known to underpredict hydrologic extremes. They're quite good at global temperature, but not as good or not as certain as Daniel talked about in terms of their ability to project future precipitation. Another issue with these GCM runs powering the model chain is this issue of computational expense that I talked about earlier. So these simulations are very expensive to run, and then you need to run them through a model like VIC and ultimately through CalSim. And so typically there are only a few realizations of different scenarios that are available for future projections. So if someone was interested in trying to estimate the range of variability of stream flow for 2050, they might only have a few samples that are insufficient to capture this extreme natural background variability that Daniel talked about. And you can see what that variability looks like from adjusted historical records within our river basins, where trends of the past century have already been taken out. And so there's this undersampling issue with these top-down modeling chains. So what do we do? There are two main strategies in the literature that prevail for dealing with this challenge of insufficient sample size in the GCM projections. And one is to use an adjusted historical record. So in many places in California, we're fortunate enough to have over 100 years of data observing stream flow at this point. So that record is fairly well representative of at least historical interannual variability. That record can be adjusted with a change factor that's derived from the difference between climate model projections and hindcasts and used to provide a good sample size for these future projections. The other approach is what's known as a bottom-up approach, which is to generate synthetic forcing time series with stochastic generators. So these are statistical models that capture the statistical properties of stream flow or past climate. And those models can be tweaked in ways that we know those statistical properties are likely to change with climate change. So we have knowledge, for instance, of this Clausius-Clapeyron relationship that Daniel talked about, thermodynamic understanding of how much more moisture air can hold, and the models can be adjusted accordingly. So I'm going to go into a little more detail because I know this is a really quick introduction to these two strategies. But I'll start with this first approach, which is called a perturbation approach. It's also called the delta change approach. This is an approach that has a long history of application in climate modeling, and to the best of my ability to trace the literature, it seems to have been originally developed as an approach to bias correct GCM output to apply it to the local scale. And by the way, when I say GCM, I'm referring to these global circulation or global climate models. So here's just a quick example with some fake data where this might represent the variability in daily maximum temperature over time for a GCM grid cell. And in this very lucky instance, the local weather station data can be recovered by just multiplying this GCM variability by a constant. But these approaches can get very sophisticated as well. And what is commonly done is a quantile perturbation, where you're actually mapping the distribution of data or the percentiles of data to projected distributions. These quantile perturbations, or these quantile-based change factors, can be developed for individual months or seasons, and this is something that can allow for changes in seasonality to be projected from the historical record. So it can actually result in these shorter, sharper rainy seasons in the projections. Some other things that are being done in climate science are quantile perturbation of the number of consecutive dry days in order to get projected droughts of longer duration, and also quantile perturbation of monthly and annual totals. This is a nice figure that shows a progression of perceived robustness with these approaches for developing future time series. And this comes from the climate impact analysis literature for studies that are focused mostly on ecology. So I was just talking about this quantile perturbation method, which kind of falls at this intermediate level of robustness. And something that's considered to be a little more robust is referred to either as quantile mapping or model space projection, where there's an additional mapping that is done from between historical observations and historical projections in order to really adjust for any biases in model hindcasts versus the observations. Okay, in contrast to the top-down approach, bottom-up stress tests are not dependent on specific GCM scenarios or assumptions around emissions. And for those reasons, for that reason, these are called scenario-neutral approaches. So this is a stress testing approach in which one of these statistical models can be used to generate forcing time series, for example, changes in mean temperature and changes in mean precipitation over a continuous range. Those synthetic time series then power the modeling chain, ultimately to look at the performance of the system. So this could be the performance of your water resource system, it could be an ecological performance metric, and so on. And ultimately, the analyst would divide these outcomes into what constitutes acceptable performance and unacceptable performance. These approaches are very powerful because they could avert poor planning decisions that would arise from a top-down approach. We've already talked about how GCM simulations are not always great at capturing precipitation extremes, and so it's important to look outside the range of what they project, and that can readily be done with this stress testing approach. Another shortcoming of a top-down approach is that the GCM scenarios represented by these crosses are discrete samples along a continuum. And so if we're comparing the outcome under a current policy versus a proposed policy, if you're just sampling at these crosses, you might miss this yellow region where the proposed policy has an acceptable outcome and the current policy has an unacceptable outcome. And you might come to the conclusion that the proposed policy has equivalent performance to the current policy, which would be erroneous. And then in this third example, we also know that GCMs have biased outputs or unrealistic dynamics. So you might think that we're operating in this region of the performance space when we're actually over here. Some other advantages of these bottom-up stress tests are that they could exclude compounding uncertainties within the modeling chain. And so, for instance, if you wanted to exclude uncertainties related to projections of temperature and precipitation, you might choose to conduct your stress testing over a change in low flows versus a change in mean flows. So really to focus on futures that arise from these stream flow signatures, like many of the ones that Daniel talked about, that we think are likely in the future. So what do we do in the Sacramento-San Joaquin Basin? Well, I'd say we're actually fairly sophisticated in terms of the approach that we're taking, particularly with DWR's recent delivery capability report that came out in 2023. So in that report, the Department of Water Resources did undertake this stress test analysis forced by a stochastic weather generator that is calibrated to the region, and then generated streamflow time series that were run through CalSim. But I will note that this is kind of a hybrid approach because the historical time series of streamflow underwent this quantile perturbation based on change factors that were derived from the weather generator forced hydrologic models. So what are other people doing? There's this great summary table of how other water resource planning studies are using climate information in this paper that I highlighted earlier by Dr. Herman at UC Davis. I read through these as well as some others that have come out more recently and some that were more focused on climate science. So I've summarized a few takeaways. The case studies mostly come from a few select places: North Carolina, England, the Netherlands, Morocco, and Australia. In the older papers, the state of the art was to take perturbed climate, so using these quantile perturbations, and using those time series to force one or two physical hydrologic models. In the more recent papers, the state of the art is really to use more of this bottom-up stress testing approach. So to use weather generator derived climate to force one or more hydrologic models. So the number of hydrologic models that are being used for individual basins is still pretty limited, but there is one standout exception in England where an ensemble of 11 regional to local scale physical hydrologic models is used, called the Future Flows Project. Interestingly, there's a limited set of studies that use purely stochastically generated streamflow that are not directly tied to climate model outputs. Rather, these are time series that model the statistical and autocorrelation based properties of streamflow in the past, and then those are perturbed in ways that climate science studies suggest are realistic for the future. So here's a couple of examples. This one's actually pretty old, from 2013, and it was focused on trying to understand how climate change might affect water market transfers in the Research Triangle area of North Carolina. And so a stochastic streamflow model was developed. The standard deviation within that streamflow model was perturbed by 10% in red and 20% in green. And then this MR time series was an adjusted time series that captured the statistical properties of the most recent decade, which featured 2 severe droughts, mean annual inflows that were 7% lower than the historical record, and a weekly standard deviation in inflows that on average was 12% greater. One other really neat example that uses these stochastically generated streamflow time series is this one. It's about 10 years old at this point. This one was one of the studies that also utilized that future flows projection of ensemble projection of streamflow for England. And so what you're looking at here are stochastically generated stream flow that results in drought-related deficits. So this drought deficit was something that could be manually adjusted in the statistical properties of the streamflow time series, as well as drought duration. And the colors are showing the fraction of simulations with an unsatisfactory state. So I think these are inspiring of potentially different ways to use climate information in water resources planning. So if we come back and ask this question of how the Sacramento-San Joaquin Delta approach compares to the state of the art, well, we do see that this perturbation approach that we use here is very common, but it's almost always applied to climate forcing data rather than to stream flow itself, which is what we do in our basin. In the literature, there's widespread skepticism about applying this method of perturbation to hydrometeorological variables that co-vary with temperature and precipitation, because when you perturb these dependent variables individually, you might not be capturing the structure of that covariance. So in thinking about our system, I think the perturbation approach does make sense given the complexity of the number of inflows into our basin. Sorry, my son is absolutely having a fit out there. So I'm a little bit distracted. So I think the perturbation approach makes sense given the poor performance of hydrologic models in capturing historical variability and spatial correlations, and as a result of the large number of basins that are in our system. But in looking towards future improvement, some things to consider might be these model space perturbations. But that's something that should be tested. And then the final question I want to pose is, what if better streamflow models were available? And I'll note that as a hydrologist, what I've witnessed in the past 10 years is a revolution in hydrologic forecasting and streamflow modeling that has really come about as a result of the availability of streamflow data from a large number of samples. Excuse me for just one moment. I need to talk to my son who's having a fit. Hi, I'm giving my talk. I'm sorry, you can have it later. You have to wait. So there has been a data revolution as a result of the integration of deep learning approaches into hydrology and the availability of streamflow from many different data points. And a classic paper that I'm highlighting is this one by Kratzert et al. In 2019, which came out in, I believe this was HESS, Hydrologic and Earth System Science. But these are showing the performance of both the national water model on all of these catchments that you see highlighted here, as well as a simple physical model in red, the Sacramento soil moisture accounting model, compared to a deep learning model, a long short-term memory model. And if you're not used to looking at these curves, the ones that are lower exhibit better performance over the range of basins. And you could convince yourself of that by looking at the 50th percentile performance. So here, the Nash, higher values of the Nash Sutcliffe efficiency are better performance. So more of these stations are performing well for the deep learning models than for the physically based models. And kind of the gold standard is when you hold out entire basins from the training process and then test the model performance on those basins. So these are effectively ungauged basins, and they're still outperforming kind of our best physical models that we have in the US. So are these models getting the right answers for the right reasons? Hydrologists think yes. We could actually look under the hood of these models, and we see that cell states, which really represent the memory of certain processes in these models, are closely mirroring observations of soil moisture and snow water equivalent. So the physical version of a catchment memory. And I'll say that the models, which are typically forced by both temperature, precipitation, and catchment attributes, never saw this data in the first place. So these large sample deep learning models really are considered to be state of the art. I think I might skip over this slide in the interest of time, but there's several ways that these are formulated. What I'll say is that a lot of hydrologists have tested ways to improve these models recently. They're not getting much better, and so the current thinking is that these models are really being limited not by their ability to capture physical processes, but by the quality of the input precipitation data. So I'll leave you with a few thoughts on some needed directions for improvement of water resources planning for climate adaptation. And one is that, I think climate scientists and people in the climate impact analysis community are really on the right track with these large ensemble models, but those models notably lack data-driven models, which are really defining the state of the art in hydrology. So there's an opportunity to expand on these ensembles with the most recent deep learning models. I think some other avenues for improvement are stress testing on modified hydrological signatures like you see here. And some of the characteristics that Daniel Swain indicated might be associated with future streamflow time series could be incorporated into these stress tests. There's a need for these studies that partition uncertainty in streamflow to different sources over a wider variety of watersheds. We need a better understanding of how common assumptions and methods, such as those that we use to perturb historical streamflow time series, might influence streamflow uncertainty. A better understanding of how hydrological signatures, like the ones we might put on these axes, may vary with climate change. And then, as Daniel was getting to at the end of his talk, the bottom line is that future streamflow is still highly uncertain, no matter what we do. And this really calls for a decision-making under deep uncertainty approach that uses strategies such as robust planning and dynamic planning. And so I'll leave you with this slide as my concluding slide. Water resources planning must combine the state of the art across disciplines. And here I've just highlighted my perception of the state of the art within these different subdisciplines. We're doing pretty well right now with water resource planning, but there's the opportunity to really take advantage of both deep learning and learning across systems from large sample hydrology as well. So that is what I have for you, and I'm happy to take questions here or in the Q&A. And I'm sorry for the interruption.
Okay. Thank you, Laurel. Interesting talk, particularly about the deep learning side of model development and application. We are a little behind schedule. Maybe we'll take 1 or 2 questions real quickly and then take a break. Anybody on the...
Check. Okay, that's much better. Hi, Laurel. This is Steve Lindley. Thanks for that talk. Will the deep learning methods remain reliable when future hydroclimate is sort of outside the envelope of what we've seen?
Yeah, that's a great question. I'm glad you asked it, and I wanted to actually have the opportunity to talk about this a little bit more. So yes and no. The state of the art for deep learning actually applies understanding that's gained from basins other than the target basin where you want to make streamflow projections. And so in addition to being forced with temperature and precipitation, these models are also being forced with information about attributes of each catchment. So the type of geology that you find there, potentially climatic regime information. And so the models are actually figuring out like which state or which set of processes apply to each catchment. And so the hope is that by doing this large sample training and learning from multiple basins simultaneously, within that learning process, you will observe dynamics, maybe from streams further south than the target basins, that might be representative of these future conditions. So that's the yes. There's a no to this answer too, though. And it's not a hard no. It's a soft no because these deep learning projections are shown to be much more reliable for short time scale forecasts into the future than for longer time scale forecasts. There's a lot of work that's being done right now within deep learning to improve these methods and make them more suitable for learning non-stationary time series. And actually, full disclosure, I just put in a big grant proposal to the ERC to work on this myself in my lab. So I'm very hopeful for the future, and I am filled with a lot of ideas on how to make these models more robust at that 10 to 30 year planning horizon. But I think theoretically it's quite doable. And I think even now, with the current models and the large sample learning, the performance might still exceed that of the physical models. But that's something that needs to be investigated further.
All right. Thank you, Laurel. Maybe next time we'll get your son onto the camera so we can talk to him.
Oh my gosh, he's kind of notorious for having a fit right when I'm giving talks at ISB meetings.
Thank you. We'll see you soon in person soon, maybe. I guess we'll take a break now. Maybe we only have 10 minutes for the break. We have this next exciting panel, Emerging Climate Science panel. So have some coffee and take about 10 minutes and then come back. Thank you. All right, let's get started again. Now we are going to start on the next panel, what we call Emerging Climate Science panel. Okay. So we have 6 excellent panelists, and we selected them based on their expertise on various climate stresses and hazards. And you can see on this slide, Paul Ulrich from UC Davis, Ben Hatchett from Colorado State. Paul will talk about climate modeling. Ben will talk about atmospheric rivers. Alan Rhodes from Lawrence Berkeley, he will talk about snowmelt. Mike Hobbins from University of Colorado will talk about droughts. Carrie Levine will talk about spatial, she's from Spatial Informatics Group. We'll talk about wildfire, another important hazard. And Dan Kayan from UC San Diego, he'll talk about sea level rise. Some of these are well-known people who have been working in these topics in this region. So let's go ahead and we will have 10-minute talks, and we are not going to have any Q&A after each talk, but after this panel, we'll have about 1 hour to have interactions with the audience. And we have about nearly 80 people online, which is quite a lot, and we will have a good exchange of Q&A. So we'll start with Paul.
All right, good morning, everybody. My name is Paul Ulrich. I am the lead of Earth System Resilience at Lawrence Livermore National Lab and a professor of regional and global climate modeling here at University of California, Davis, and the lead of various Department of Energy projects, including the Program for Coordinated Model Diagnosis and Intercomparison, or PCMDI, which has been involved in climate model evaluation for a fairly long time at this point. I'm going to talk very briefly about climate modeling and then give a very quick rundown of kind of the big climate variables from the meteorology, from the atmosphere side for the Delta, including their projections into the future. All right, first of all, as we've heard already, most of our climate projections into the future come from global climate models, or GCMs. These are generally produced at about 100-kilometer grid spacing, which would basically be one grid point for the whole San Francisco Bay Delta. This is obviously not fine enough resolution for us to really make decisions at the decision maker scale, so we often rely on methods known as downscaling in order to actually take those coarse resolution global climate model outputs and turn them into finer scale projections and data that we can then use. Most of the model data that we use for these inputs right now comes from the Coordinated Model Intercomparison Project, which is coordinated by the World Climate Research Program and feeds into the Intergovernmental Panel on Climate Change's assessment reports. That data is, of course, publicly available, and we're currently in the CMIP 6th phase, or the 6th phase of CMIP, but we will be moving soon into the 7th phase, and we're starting to put together some of those experiments for that phase of the project as well. For the most part, climate model outputs have been fairly consistent since about CMIP 5, and we're seeing about the same response for most of those climate models when it comes to future projections. And so we're really kind of in a point of diminishing returns when it comes to our ability to project things at the global scales, but we're continuing to learn a lot at the regional scales using a variety of different regional climate projection techniques. Using those CMIP outputs, we basically zoom in using downscaling methods over limited regions, and this has been done extensively over the US and over regions globally in order to produce these very fine resolution outputs, often on the scale of maybe just a couple kilometers of grid spacing, which really allow us to then get that really, really fine view of how climate change may be impacting us on local to regional scales. There's a variety of different approaches that we use for this downscaling, and it's nice to have this variety of approaches so we can cross-compare and understand how they differ relative to one another. The overall flow chart that is shown here shows how we take those Earth system model outputs or global climate model outputs at the top, and how that information then flows into a variety of techniques, including statistical downscaling, dynamical downscaling, and hybrid downscaling type techniques. Historically, we've used statistical downscaling mostly at these fine scales because of the fact that downscaling itself can be very computationally intensive. And using regional climate models, that is basically simulations of the climate system at very fine scales, can be very computationally expensive and make it very difficult in order to run the kind of large statistical ensembles we need to get confidence in those future projections in order to really build, good statistical distributions about how things may be anticipated to change. New methods have emerged recently, including hybrid downscaling techniques, which will actually take the outputs from those dynamical downscaling models and use those to train statistical models as well for those projections. We are very fortunate right now, actually, in our current age, to have a large variety of different data products now available that can actually provide us with very fine scale information on climate change, even in the San Francisco Bay Delta. These include a variety of statistically downscale products, dynamically downscale products, and a new hybrid dynamical project, or a new hybrid downscale product, which I will be focusing on for the remainder of this talk, and is being fed into the California Climate Change Assessment right now in order to provide its information on projected changes. But unfortunately, we're also left with so much information that it is very difficult in order to deal with that much data and see what the reasons are when there are disagreements among those products. And some of the work that our group is doing at Lawrence Livermore National Lab, as well as here at UC Davis, is aiming to understand how the model spread actually plays in confidence of future projections and how we can leverage that information in order to build confidence around that data. And I'm happy to talk to anybody about that later. As mentioned, the method that I'll be focusing on for this talk is the LOCA method, localized constructed analogs, of which Dan Cahan, who is here, was one of the co-producers of. And it comes from UCSD, developed by Dave Pierce, who is unfortunately now retired. It's very sad because he has been so fundamental, so key, I would say, to projections of climate, particularly here in California. But that has now been picked up by our colleagues at Lawrence Berkeley National Lab, and hopefully Dan Feldman will be able to carry on the legacy and build future versions of localized constructed analogs going into the future. This method is very unique and very easy to justify. Basically, what we do is we look at climate model outputs, take that coarse resolution climate model output data, and try to identify a day historically that had a similar climate state to what that model was producing, and then take the fine scale data from those historical dates and use those in order to actually build up a high resolution analog map of what the fine scale data associated with that coarse resolution projection could be. This is how LOCA 2 US and the original LOCA product was actually trained in order to produce data over the contiguous United States. This newest data set, LOCA 2 CA, available over California, available at 3-kilometer resolutions, actually is a hybrid downscaling technique, leveraging the Western US dynamically downscaled data set produced by our colleagues at University of California, Los Angeles, at 3-kilometer resolution using the weather research and forecasting model, using that as training data so that we can have data both historically and into the future, and can use that in order to identify those corresponding analog days. All right. So I can ramble for probably an hour about different downscaling methods, and that would be a lot of fun, but I have a limited amount of time and you'd probably get pretty bored pretty fast. So let's talk about climate change projections for the Bay Delta. We're very fortunate with the timing of this meeting in that we have been working very hard over this summer in order to produce some very compelling figures about future change in California, and many of these have been localized to various regions, including the Bay Area Delta here in California. And so I will have some very nice eye candy looking figures for showing those projected changes and what we've seen historically. Starting things off, here is the historic annual average temperatures obtained from the NClimeGrid dataset, a gridded climate data product over California that shows that we are in the midst of things. Things have become hotter, particularly since the 1980s and over much of the 20th century. Things have become much hotter recently, in particular with 2014, 2020, and 2024 being among the hottest years on record, with the expectation that we'll see those extremely hot years, those record-breaking years, become more and more frequent into the future. Here are projections of change using our global climate models. This shows the likely range among 3 different climate scenarios. Our kind of fossil-fueled scenario, SSP 585, which is kind of a worst-case type of scenario, and all the way down to SSP 245, which is a lot more optimistic. In all cases, we see warming and consistent warming in all those scenarios, although we see different leveling off by the end of the century. Notably, almost all these scenarios are statistically indistinguishable by mid-century. That means it doesn't matter which scenario you pick, we're pretty much locked in terms of our mid-century projections of change. But by end of century, that's where we really see those differences, with these models ending up at 3.5 degrees, 5.5 degrees, and 7.5 degrees Fahrenheit above the baseline 1981 to 2010. So there is a long-term role in terms of our scenario selection in terms of those effects. However, this effect is not spatially uniform. Here we see the number of days per year with maximum daily temperatures above a particular threshold. And what we're seeing is that the majority of the year will be above 80 degrees Fahrenheit during the day in the Bay Area Delta by even mid-century. And what we're going to see actually is 10 to 15 days per year above 110 degrees Fahrenheit through the Delta, which is essentially zero over the historical record there. Heat wave durations are expected to increase using the basically 98th percentile of temperatures historically. If we look at how long those periods have lasted historically, it's been about 3 days. By mid-century, that's going to be about 7 days of temperatures over that historic threshold. And by end of century, it's going to be more like 13 to 15 days in sequence, consecutive days where we have these extreme temperatures. When we turn our attention now to precipitation projections, what we saw in Dan Swain's talk earlier is that the results are much more muted. Precipitation is expected to be fairly uniform, and there's a lot of disagreement in terms of the sign of that overall change. In general, it's pretty consistent that we don't have a statistically distinguishable signal when it comes to overall annual mean precipitation change into the future. There are some changes, though, in variability. What we're seeing is much more frequent extreme wet years there at the top, passing above that historic dotted threshold for extreme wet years, and slightly fewer, although it's kind of basically there's no statistical signal there, on extremely dry years. This indicates that that whiplash effect that Dan had talked about earlier is primarily driven by a significant increase in the number of extremely wet years. And you can see that as we go down to finer scales, when we look at the extreme rainiest day of the year, we see a very clear signal actually in that trend on the order of about 20% more precipitation on that wettest day of the year. And so what we're going to see is much more extremes into the future because of the climate change effect, while we see a much more muted response in mean precipitation signals. Notably, these differences are not uniform over the course of the year, and Dan again kind of alluded to that with the sharpening of the seasonal cycle. However, if you also look at temperatures, actually, what we see is that the expected temperature change through the end of the century is almost double in the summer season compared to the winter season. So those annual mean temperature changes don't tell the whole story. And actually, when we have the hottest temperatures, we're going to see in August and September in particular, a exacerbated influence from that temperature change. When it comes to precipitation change, almost all of that precipitation difference is isolated to January and February, where we have a very clear signal of enhanced precipitation, with slight drying basically occurring in the fall and spring seasons, and as a consequence, basically a much longer dry period throughout the year. All right, that is the very, very quick rundown, and I will turn it over to my colleagues then in order to go into some details about those projected changes.
Ben will talk about atmospheric rivers and precipitation.
All right. Thank you, everyone, and thank you for the invitation to come speak and share some work that really has been largely led by Sasha Gershinov and a long cast of characters, recently putting together a manuscript that is now in press and live on the San Francisco Estuary and Watershed Science website. So I'll be summarizing a lot of this work, as well as adding some additional thoughts and pieces that we weren't able to touch on due to some of the limitations in manuscript lengths that I'm sure you all have lots of fun with. So we'll be talking about atmospheric rivers, the narrow corridors of concentrated water vapor transport found on the equatorward side of mid-latitude cyclones that are really our gift and our curse. They give us all the water resources that we need to be the, I believe, 4th largest economy in the world, but also produce the droughts and floods that we must manage. And through the process of these few events, or few too many or few too few in a given year, we have many choices to be made over the next few years and continuing into the future about ways to manage our ecosystems and our economies in a way that achieves multiple benefits, protects life and property, and restores the ecosystems that we rely upon. Let's see. So perhaps my favorite quote from the paper, that I don't think this comes as a surprise to anyone, but I think there's a lot of value in reiterating that to go forward, we have to learn to derive more of our future water resources from a less reliable snowpack, fewer storms that are becoming more intense, and as a result of that, we're going to be seeing more punctuated groundwater, or sorry, we'll get to groundwater, more punctuated floodwater going forwards into the future. And of course, that need exists amongst this background warming and drying, the thirstier atmosphere, infrastructure that is getting older and is perhaps questionable at best. And we also have some new infrastructure that is pretty awesome, trying to achieve many management objectives, and as we've been hearing throughout the day, a tremendous amount of uncertainty. However, as Paul mentioned, these results are very consistent, and they've remained consistent over time, and I think we can take some solace in that. The individual events or efforts, broader syntheses over time have really found very consistent results and are allowing us to dive deeper into some of the nuances. So where I want to go with this is talk about where we're at and some directions of where we can go. So a few of the favorite improvements that we've been making over recent decades have been really in this modeling side, as well as some of the tactics that we use, or these storyline approaches, these case studies that have now been transitioned into ways that we can really understand how things work better. So from the modeling side, improving our physical process representation has allowed us to really dive more deeply into how atmospheric rivers and storms in general are changing, as well as droughts and other natural hazard causing weather and climate events. And that really transcends scale. We're able to better capture these physical processes from planetary or synoptic continental scales down to the mountain range scales, and then increasingly so to the watershed scales, where we can really see how different events manifest themselves at actionable spatial and temporal scales. That's come not only as an improvement in our physical parameterizations and our ability to represent the natural world, but by also improvements in computational resources, and as a result of that, improving the resolution that we're able to simulate these processes. And that leads us to better understanding of how these changes and interventions to mitigate negative changes influence management and decision-making processes, infrastructure, and also kind of highlight the value that we'll get to as well on monitoring and networks and other ways to measure change and test and assess how well our adaptation strategies are working. So a major conclusion from a lot of the work over the recent decades that is being reiterated through time and again is we expect fewer but more intense storms with potentially greater clustering. And I think that's a recently discovered nuance that is particularly valuable to understand, that we're not just going to see fewer storms that are stronger, but they may become closer together in time. That will lead to potentially a great increase in runoff during those events. Thinking about the 1997 flood event, the New Year's storm that happened almost 20 years ago at this point, we expect to see in the mid to later century an approximate doubling of the likelihood of storm total precipitation. That's across 14 models. So another type of very problematic storm, similar to the 1862 storm, where we are seeing, with a warming background climate, an increase in the likelihood of that taking place. We also know that sequential storm events can be quite problematic. So 97 was an example of that. More recently, 2017, 2021, 2023. These are problematic because as storms line up across the Pacific and we start saturating our watersheds, becoming very efficient at producing stream flow and runoff, we're running into challenges with our infrastructure and our ability to deal with that water. So projections, there's been a few papers on this and a lot of room for more work due to some of the timescales that pick out what is a sequential event or not, but we do expect increases in these sequential events to take place. We also know that storms are becoming warmer and they are becoming more rainy and less snowy. That also is more efficient at producing runoff. And something that Mike Anderson mentioned to me years ago that I think is still a very salient point is that we're now having to manage these storms as more of a hazard rather than a resource. That wasn't how they were initially our infrastructure was intended or our agreements, but this is something we're dealing with. Because we still have cool enough temperatures to produce a generally historic range of snowpack variability, as the climate warms and storms are becoming warmer, we're in this, what we call a peak rain on snow period, where we have this large existing snowpack, kind of a lurking hazard in the mountains, and the potential for larger, rainier events to take place, thereby increasing the rain on snow flood potential. Work led by Tamara Shulgina suggests that in addition to this continuation of a snow to rain transition, that we're going to see an increase in the atmospheric river-derived precipitation during the cool season in the mountains in a way that really kind of captures the hypsometry or the distribution of elevation of how much topography we have at given elevations. And some of the largest increases in the total amount of precipitation accumulation are occurring right at that current rain-snow transition, those mid-elevations, kind of right around that Lake Tahoe level. And so we're going to see, as that snow line increases, an increase in atmospheric river-derived precipitation that is going to be now falling as rain rather than snow. That's going to lead to, by around 2050 or so, an estimated 1.5 million acre-feet of snow water equivalent that is now lost or not existing as snow, that's going to be realized as midwinter runoff, leading to the need to manage that to achieve multiple benefits in a different way than previously planned for. Some of the operationally relevant progress in the physical science perspective is, I think we're able to now move further into nuance and more to both system-wide understanding and watershed-specific understandings, utilizing integrated or coupled groundwater and surface water models and other very comprehensive management experiments are allowing us to ask better questions or more detailed questions that can then tie into management decisions. So an example of that is, what are some of the implications of changing atmospheric river characteristics or flood implications for groundwater? Work led by Erica Cirilla Woodburn used a coupled model in the Cosumnes watershed and an atmospheric river tracking approach, as well as a particle tracking approach to identify where water from different sources, either atmospheric river storms or other storms, moves through the watershed. You can think of that as kind of a glorified rubber duck experiment to see where that water is moving to. So breaking that down by different storms during a wet year, 2017, she was able to identify that there's very different trajectories of water that's derived from different kinds of storms. She found that approximately 3 times less groundwater is derived from atmospheric river events than non-atmospheric river events. With an expectation of more of those in the future, that's going to lead to some implications. There's been also excellent progress in the subseasonal timescales, the week 2, 3, 4 timescales of atmospheric river activity, and that gives us more time to make decisions going forwards. If we want to do forecast-informed reservoir operations, it's important to understand, is it going to be dry for the next couple of weeks? Can we hold on to that water, or are we expecting another wave train to set up over the Pacific and drive additional events into the region and therefore have to deal with that water in that way? So currently we're seeing some pretty good skill out about just over 2 weeks, which is a notable improvement in the recent decades. From the social science perspective, I think that's where we can make pretty substantial progress, utilizing social science to understand and assess knowledge sharing, decision making, and how partnerships are produced and exist throughout the management cycle will really be able to help us translate scientific changes and understanding into action. Of course, that requires time and communication. We want to move through this process from people cooperating, maybe they coordinate, hopefully they collaborate, and eventually they will co-produce, and we can see some very notable goals that take place from that. And I think the atmospheric rivers and management and infrastructure really tie that together nicely as we're improving our forecast lead times and improving our physical understandings. Now we need to move into how to get that information to make decisions at longer lead times to open up space for pulling the lever on the dam, if you will. A remark to make about the need to maintain and expand our observational networks, which are just paramount for monitoring change, verifying models, and really measuring success of our adaptation. What's changing? How fast? Where? Are we meeting our objectives? Utilizing an after-action review approach to see what worked well, what didn't work well, what to do better would be great. We need to continue long-term records of weather and climate to understand how things are changing at different timescales. Maintaining our newer networks. DWR and NOAA have invested pretty substantially in networks throughout California. Satellite records need to be continued. Soil moisture and snowpack. These are all different kinds of records that can really help us understand, as well as increasing our development of new data sets. And I think citizen and community science, we have a project with rain snow observations in the mountains to involve the community, show them how their work impacts the science, and really get their buy-in on understanding why we're doing the management decisions that we are. Through that, reporting back is very important to the community, telling people why we're doing what we're doing, what questions we're answering with this, what are we learning, and why does it matter? I think this Central Valley Flood Protection Plan did an amazing job with this, highlighting numerous partnerships, projects, and policy spotlights throughout. We need to do that more. We need to get people involved in this science to operations piece. So with that, I will turn it over to Alan. Thank you very much.
All right. Next, we have Alan Rhodes from LBL, Snowpack and Snowmelt.
I think these are your backup slides, then? Okay. So, hello everyone, my name is Alan Rhodes. I'm a research scientist at Lawrence Berkeley National Lab, and I'm very humbled and honored to be able to speak to you today. I'm representing kind of the snowmelt side of the equation and its impacts on the Delta. And just wanted to highlight my dog child, Luna, there, taking in a local reservoir in Auburn. So it's probably a little bit overkill to go over this in this audience, but mountain snowpack acts as this large natural reservoir that essentially provides a free service for us and nearly doubles our reservoir storage in the state. So this diagram here is just showing the interannual variability of peak snowpack, which typically occurs on April 1st of every year, relative to the largest reservoirs in the state. And so we really rely on this snowpack to essentially provide us with double the amount of water, and it is released gradually over time into the seasons in which demand is highest. Unfortunately, that natural store of water, due to anthropogenic climate change, has become less reliable as a natural store. So these are showing trends across the Western US in our observational stations like Snowtel, for example, which shows that about 90% of stations since the 1950s have seen a decline in April 1st snow water equivalent. That 23% decline is essentially the volumetric water amount equivalent of Lake Mead. So we've already lost a substantial amount of natural reservoir capacity in current levels of warming. And unfortunately, also that peak timing at which we get our peak snowpack, so traditionally April 1st, is moving about half a week to a week earlier for every degree C of warming. And so in one of our most recent papers, it was a synthesis of the literature looking at what do the projections hold out to mid-century and end-century for mountains around the world, or sorry, mountains around the Western US. We found that we could see a comparable and similar decline of about 25% by 2050 and upwards of 50 to 60% decline by 2100. And unfortunately for the Sierra Nevada, it seems to be one of the mountain ranges in which the snowpack decline is actually more accentuated than other regions, primarily because of the fact that we rely on atmospheric rivers, which are relatively warmer storms, to provide that buildup of the snowpack. And so that gradual decline in snow over time doesn't mean that extreme events can occur within that gradual decline. And so this has been touched on by previous presenters, but Essentially, in historical climate, we maybe get a rain on snow event maybe once per year, a couple times per year. But in a warming world, as we transition from more snowfall to rainfall, and when snowpacks are more ripened and susceptible for extreme melt throughout the entirety of the snow season, potentially, you might have more punctuated, flashier runoff events. And also because rainfall creates abrupt runoff, that can also create abrupt runoff responses into our reservoirs. So to kind of contextualize these effects of a changing snowpack, atmospheric river dynamics and things, in recent years in projects I'm associated with called the Hyperfacets Project at the Department of Energy, we've been using these storyline approaches to kind of contextualize what might be expected with future changing snowpacks, snowmelt extremes, et cetera. So we chose to recreate the 1997 New Year's flood event in our virtual laboratory, the Energy Exascale Earth System Model. And this model, what's really neat about it is you can telescope resolution within it down over, say, places like California to resolve the topography much better and to represent these kind of rain on snow risk regions with more fidelity. And we chose this event because it's essentially the 1 in 100 to 200 year event. It's something the Department of Energy, or sorry, Department of Water Resources, some stakeholders we have on our project have said that they can kind of manage for this sort of event. And so they thought it would be very valuable to see an event like this recreated in these virtual laboratories. And unfortunately, it's one of the costliest flood events in California history as well. It displaced about 500,000 people. 43 of the 58 California counties were declared disaster zones after this, had ramifications for agriculture. And as it's maybe hard to see here, but that's Yuba City and Marysville there. And fortunately, the levees were resilient to the floodwaters that came down the Yuba River, but it was a near miss. And then in iconic places like Yosemite Valley, that's a picture of me actually at a sign commemorating how much floodwater occurred in that valley, but it's about 8 feet of water, about a shack's worth of water that inundated the whole valley. So it was pretty remarkable. So with these virtual laboratories, we can skillfully recreate the event that was. That's the control experiment on the left. This is showing snowpack animated over the lifetime of the 1997 flood event, which occurred over about 4 days. And you can kind of see that in the kind of event that was, snowpack is built up in the months prior, and especially in the northern parts of the Sierra. But as we move to a 1.7 or 3.5 degree world, we start to see less antecedent snowpack available to melt, but a flashier and more ripened snowpack at the central and southern parts of the Sierra Nevada at higher elevations that can then potentially lead to more rain on snow risk further down south, where we have less monitoring networks, less resilient infrastructure. And so it's really shifting this rain on snow risk and the heterogeneity of that response further south, which I think presents unique challenges. And just to kind of show this, these are change diagrams of the antecedent snow water equivalent, so the amount of water in the snowpack. On the first row, we also looked at recreating this event in a pre-industrial climate. So what essentially one wanted to answer is how much has climate change to date shaped the changing snowpack, or the snowpack response and the runoff? And what we actually found is that climate change negligibly influenced the 1997 New Year's flood event, at least up to this present day of warming. But once you start to get to 1.7 and 3.5, that's kind of that peak rain on snow concept that Ben brought up, where you start to see a flashier snowpack, maybe less snowpack in the northern parts of the Sierra that can melt, but a flashier, more ripened snowpack in the central and southern Sierra, which presents different challenges. So although you might see more runoff on average, there is spatial heterogeneity that really matters, especially where we've put our infrastructure. So in that paper and in several papers since, because of my engagement and co-production with practitioners on the Hyperfacets project, I'm trying to not only put the science and the take-home messages, but maybe the implications for management side of things. So the 4 key things that we found in this study is that peak rain on snow hazard potential might be accentuated at about 1.7 to 2.5 degrees of warming, especially if a 1997 flood-like event reoccurred. Rain on snow events could include more intense short duration rainfall. We heard about this earlier with the Clausius-Clapeyron effect. So you might get nearly the same amount of storm total precipitation, but it's going to come in more bursts, and it might come more kind of condensed together. Precipitation scaling with warming, if you look at the storm total it's sub-Clausius Clapeyron, but if you look at sub-hourly, it's super Clausius Clapeyron. So that I think has important implications for engineering IDF curves and design standards and things like that. So we need to start rethinking scales of how precipitation changes at sub-daily and out to storm total amounts. And again, flood hazard might shift more from the northern to southern portions of California, Nevada, and there might actually be more enhanced lee side spillover where the precipitation events can go over the Sierra Crest and actually, unfortunately, produce more rainfall in places like Reno, Nevada, which also was very much inundated during the '97 flood event. So that is one flavor of future snowmelt extremes that might occur. Another one that I've most recently started to dive into are these things that we've coined as snow eater heat wave events. It's a cutesy term, but we're trying to say essentially that it might not be a traditionally defined heat wave event like 95 degrees Fahrenheit for 3 days in a row, but it's enough of an anomalous heat event that it lead to a ripened and abrupt ablation of the snowpack. So a storyline for this sort of snowmelt extreme occurred in 1983, where an abundant snowpack had built up in the months prior to this event, and then during 4 days in late May, early June, all of that snowpack was ripened and abruptly melted, and places like the Salt Lake City had so much flood water from that snowmelt that they needed to create 2 artificial canals to convey the water out of downtown. And the Great Salt Lake also rose by about 4 feet after that event, so it was pretty remarkable. Even more remarkable, and I couldn't believe this when I first saw it, is that one of the largest dams in the western United States, Glen Canyon, had so much flood water behind it that the engineers needed to actually make what they call flashboard, which is a fancy term for plywood reinforced with rebar or with metal to make sure that the water did not overtap that dam. And so you might imagine that these sorts of snow heat wave interactions might start to occur more at mid-century as well. And so in this analysis, we wanted to see how much climate change has maybe changed the trends in these snow eater heat wave events. We also needed to come up with a workflow that can identify these events. And then we wanted to see how well our operational snowmelt models represent the flood or the meltwater in these events. So what I'm showing here is just a glimpse of one of the results looking at the 1983 kind of snow season. In black here, this is the SNOTEL observations across the west. The black bold line is the mean DSWE, negative DSWE during the event. We identified the snow eater heat wave event in that gray region. And what we showed is that in general, our operational snowmelt models can represent that mean melt, but the extreme melt, which are the thinner lines, it's a lot more constrained, meaning that we might not, in our operational models, be able to represent these melt events very well. So we might be essentially flying blind. So we proposed some add-ons to this operational snowmelt model, SNO 17, in this paper that's still in review. And it's not necessarily the right answer, but we're trying to see how we can better incorporate the effects of snow eater heat wave events into these operational models. But essentially what we found is that 7 of the 11 spring snowmelt dominated, so not rain on snow dominated superfloods since the 1950s can be linked within 5 days of one of these snow eater heat wave events, which we were able to come up with a framework in identifying them. We found that melt season snow heat waves typically on average double the snowpack loss that you get. But there's still questions on where does that snow go? Does it come out abruptly as melt? Does it come out as sublimation or a combination of those? Because that really matters for water management if you lose that water that you thought you had from the snowpack later on in the year. Extreme melt rates are underrepresented in operational snowmelt models, which has important implications for water management and kind of using things like forecast informed reservoir operation or other things where you might not be expecting as much meltwater as is coming into the reservoir. And because we use a long-range reanalysis to do this analysis, since the 1850s, we found that Western US snow eater heat waves have increased in area and frequency, decreased in duration, and actually shifted earlier in the melt season. And so this quote here, I think really nicely summarizes both what Ben was talking about and what I've just talked about, that California must learn to derive more of its future water resources from less reliable snowmelt, fewer storms, and more punctuated flood water. And to be kind of proactive rather than reactive to this, these are kind of 5 things that I think need to occur, and a lot of the speakers thus far have already talked about this, but maintain and expand monitoring networks, and particularly leverage new remote sensing techniques like the airborne LiDAR capabilities, the Airborne Snow Observatory. I also think that we need better measurements of cold content. Cold content is essentially the amount of energy that would need to be overcome in the snowpack to make melt occur. And I think we really don't have good widespread estimates of that cold content, which is really a good indicator for when extreme snowmelt might occur during these rain-on-snow or snow-to heat wave events. More nimbly managed infrastructure, so using things like forecast-informed reservoir operation combined with flood-mar could be really beneficial. Bake more water in the ground, more efficiently utilize that water and generate new water, such as direct potable reuse. And then this might seem obvious, but fostering more partnerships between academia and management where we can talk about these things more regularly and build these proactive responses. And I think just a very specific example of what that might look like is doing scenario-based training and exercises with these storyline event approaches, with the kind of virtual laboratories that we have, to look at things like more clustered extreme storm events, look at more of these, what happens when these precipitation bursts with more rainfall occur in the headwaters of reservoirs. How do we manage for that more proactively? Maybe less snow, but a more active snowpack. So looking at how cold content erodes, how fast that erosion occurs, and then looking at the kind of melt versus sublimation during both rain-on-snow versus snow-eater heat wave events, because if that water is lost in the atmosphere, comes out abruptly or is absorbed in the soils, that really matters. And I also think looking at unintended consequences of FIRO combined with flood-mar, meaning that if we get more atmospheric rivers that are rainier, create more precipitation bursts, if we convey water that we want to store in the ground to an agricultural region or a floodplain, how long does it take to percolate down into the groundwater? And would that create unintended consequences of another atmospheric river in close sequence, creating precipitation bursts, creating localized flooding? So I think those sorts of unintended consequence modeling could also be very useful. So with that, I'm going to turn it over to Mike and really appreciate your time and attention.
Thank you, Alan. Next, we'll have Mike Hobbins, University of Colorado Boulder, to speak about drought, also nexus to wildfires.
Okay, thanks. So I'm really going to talk about the demand side of drought here, and anybody who's been following my career, and why would you do that? Anybody who's been following my career will recognize just this continuous love song to evaporative demand, which is going to be the subject. I've got a few colleagues here who you probably know better than you know me. I'm sorry the font is so small, but let's go. So I was asked, one of the questions was, how do you recognize gaps, or what gaps have you do you know that can inform decision support models? So that's really where I'm focusing this. I'm not going to spend a lot of time on just explaining what evaporative demand is. Thankfully, I don't have to do that, I don't think, to this, so I might skip over some slides. But here, obviously, drought is just an imbalance of supply to the surface and demand from the surface, right, to the atmosphere. And traditionally, obviously, physically, it's precipitant evapotranspiration is what you want to look for, as that's actual ET. But traditionally, what we've done is estimate the evaporative loss by a function of temperature, using PETs that derive from basically are temperature-based. We may not do this in this room, or we may not do this in coupled our Earth system models, what have you, but you'd be embarrassed to know how many people do this operationally and don't even recognize that they're using temperature-based evaporative demand models. So we're not going to do that. We're going to use, what we do here is use a physically based evaporative demand, and we're going to use Penman-Monteith reference evapotranspiration for a variety of reasons, one of which is the formulation is differentiable, which will become important later. So what does it look like when you run Penman-Monteith and you force it by, say, NL-2? Over the United States, it makes sense. Where it's hotter, windier, drier, or sunnier, evaporative demand, the thirst of the atmosphere, is highest. Where it's cooler, wetter, less windy, say in the Northeast, it's lower. Our input data that we generally use are air temperature, specific humidity, sunshine, and wind speed. So this is the take-home. We all know this. Evaporative demand is the thirst of the atmosphere. It's not actual ET, it's how much evapotranspiration could take place were moisture available. And my point here is to talk about how useful that could be to us in examining drought. So we recently came up with this, Paul Kukal at the University of Idaho formulated this idea of thirst waves. It's similar to heat waves. It's evaporative demand above the 90th percentile for 3 days. It obviously has very important agricultural effects. Not quite a drought necessarily, because you may not see impacts beyond plant physiology. but it's the precursor of drought. And I don't work in California, but what I've tried to do is extract some sort of take-homes for what's happening in California. Clearly, right now, we're very exposed to these thirst waves. We have the highest intensity across Kona, so 1 to 1.3 millimeters per day. That's a surplus. The greatest number of events. And the trends are that the intensity is going to increase significantly. The near mean increase in duration it's not significant. It's very similar to what's going on across the rest of the country, but a near maximum increase relative to the rest of CONUS in the number of events. And this paper just came out. So that's California, or the Central California counties. This is not important for this audience, I don't think. Evaporative demand increases in drought, whereas actual ET increases and decreases. It makes evaporative demand a very robust measure of drought. That's important moving forward, but that, I think we all understand that. So how can we use evaporative demand? Well, what we've done at PSL, NOAA PSL, and University of Colorado is generate EDDI, the Evaporative Demand Drought Index, that looks only at evaporative demand and compares evaporative demand over a bunch of timescales to its climatology, and basically ranks it and assigns a percentile. And what we're showing here is is the EDDI for the 2-week EDDI. It's a multiple timescale tool for last week. And you can see we have drought in that's the San Joaquin Valley, I guess, in Southern California. Okay, so this is how you read the EDDI map. Blue is it's wetter than normal. The evaporative demand is lower than average. Warm colors indicate that it's higher than normal. The atmosphere is more thirsty than normal. Okay, so EDDI is useful for a variety of sectors in droughts. It's good for farming, ranching. It also has interesting use in hydrologic drought, and I'll show you an interesting example about that. Also very excited are the people who work in wildfire monitoring, wildfire planning. They're very excited about evaporative demand. So I'm trying to skip through to a bunch of different tools or applications that we have in evaporative demand, but this is one particular to the Central Valley of California. This is Dan McAvoy's work, and he looked at 6-month EDDI on April, the end of April. He looked at 6-month EDDI and compared it to 12-month standardized runoff index that was available much later in the year. So after the entire year, what was the standardized runoff index and what was the 6-month EDDI available 6 months earlier? And you've discovered that only 6 months into the water year, you had 72% of the variability explained in runoff, using only evaporative demand. So that's early warning right there. That's early warning of hydrologic drought. So you can imagine that would be useful for people who are interested in the Delta smelt or all your hydrologic, ecological requirements down in the Delta. So we're very excited about this in Delta. So can EDDI monitoring snow drought? That's a good question for us to ask. And can we predict low flow, stream flow later in the summer? Recall, EDDI has no precipitation input. This is just evaporative demand. It's a very powerful tool, I think. Okay, other applications of evaporative demand, we look at flash droughts. It may not be that important for California. There was a flash drought in your very large, was it the 4-year drought. So there was a very strong intensification of the drought that happened about 2 years in, and that became a flash drought. But we see that EDDI, using evaporative demand only, leads the US Drought Monitor in identifying flash drought. By leads, I mean it recognizes it ahead of time. Okay, so we use that to generate a tool, which is the results are shown on the right-hand side, this 2-week EDDI-based flash drought monitor, and we published it to great acclaim in Nature Climate Change, but people have started to use this and they really shouldn't. This is actually a point of embarrassment for me. I generated that tool and it doesn't really work. So you need a bit more nuance and complexity involved in recognizing flash drought. It's not just looking at how fast does EDDI change and by how much. That's not sufficient. So there's work to be done in recognizing flash droughts using EDDI. But here we come to the drought-wildfire connection. There is such a strong relationship between evaporative demand and fuel moisture across, here we show the Southern California GAC. The GAC is oh goodness me, I can't think of what it means. Coordination Center is at the CC, I think. It's an area basically of almost all of Southern California, basically. Very strong relationship between evaporative demand and fuel moisture. And what we show is any drought index that uses evaporative demand outperforms indexes that don't in terms of matching fuel moisture. So that's important for wildfire predictability. Okay, so this is actually something I really should have spent more time on, describing the background behind this graphic. This is the Tubbs fire, presented from the point of ignition. And what we're looking at is the progression of the fire. The vertical line is the fire, and then while the fire is burning off to the right-hand side. And what we're seeing here, the black line is the evaporative demand anomaly relative to the 40-year climatology that preceded, at that point of ignition, that preceded the fire. And you can see there's this massive spike in the black line. There's two spikes in the black line. The other colored lines are those four inputs into evaporative demand. There's, as you can read, there's temperature. The red is, apparently it's a touch screen, sorry. The red is temperature, and just look at the temperature and look at the blue, the Q, which is humidity. So what we see here is these two spikes are first, before the fire, driven by temperature, and then temperature declines and evaporative demand approaches normal again, and then there's a humidity-driven spike right at the fire. So this is all well and good, but what this means is that we can decompose the demand side of drought. We can do it analytically, and we can do it in real time, and that's something we're starting to do now. We're starting, well, the paper is in the works. We haven't submitted it yet. It's on the way. But decomposing the demand side of drought not only is good for drought, it's also good for wildfire. And the wildfire community, like I said, is very excited about this sort of decomposability of evaporative demand. Okay, so moving forward, this is work by Andy Hoyle. I am not going to try to decode this very beautiful graphic on the left-hand side, but basically what he did is he looked at large fires, extensive areas burned, sorry, that's what he called it, under La Nina and El Nino conditions for 1984 to 2022. And he compared it to elevated evaporative demand or below average and elevated or below average precipitation. But what he found was that this is for the Northern California GAC. So this is about the scale of a GAC. You can see it goes from Oregon down to below the, like San Jose, I guess. This is for the Northern California GAC, that both phases affect the wildfire, the risk of extensive area burned, both La Nina and El Nino. La Nina, because the hypothesis being that you start with cooler, wetter conditions with La Nina, which fosters vegetation growth, and then the wet conditions shut off, and you get an increase in evaporative demand, and that dries out the fuels that just grew, and then you get more burning later in the year. So that's the one hypothesis for the Northern California GAC. And El Nino has different qualities. It decreases the area burned risk, apparently. But did it again, sorry. The idea being that if we combine this with that decomposability that I demonstrated in the last graphic, we can really start to uncover what exactly is driving this increase, driving an increase in evaporative demand, and combine that with precipitation and uncover predictability of wildfire using evaporative demand. So that's one thing we're very excited. This paper hopefully will come out later in the year or maybe in the new year. So finally, you all want to talk about past and future trends. I'm not a climate scientist, but here's a graphic for you. This one on the left, this is a paper that just came out last year in Science, looking at ERA5, trends in evaporative demand and drought, precip minus evaporative demand across the Western United States. And it's really the latest in a long series of, like a pantomime of papers that demonstrate there's no effect of warming on drought across Western United States. Oh, yes, there is. Oh, no, there isn't. Oh, yes, there is. And it's been 20 years of this back and forth. But we are consolidating around a consensus that, of course, there is an effect on drought across the Western United States. And here, what they show using ERA5 is the intensity is up 35% and the area is up 17%. And the contributions from evaporative demand exceed the precip deficit. So that's very interesting. Once again, we're decomposing this drought, supply versus demand. Demand is more important than supply in this drought severity. So that's the past. In the future, this is just a graphic we pulled off. I had my friend Imtiaz pull off for a point that's just like about a mile down the road. Looked at 30 years, 40 GCMs, and it's comparing 1971 to 2000 to 2051 to 2080. And you can see that this is, what we're showing here is the actual ET rates on the bottom and the potential ET rates, or the evaporative demand on the top. What we show is that we go from blue to red. The actual ET doesn't vary that much, but the atmosphere becomes much drier. It's up drier by at least 1 millimeter per day. So what does this mean? This means we're in a more water-limited hydroclimate. What does that mean for drought? That's an open question. And that's where I'm going to leave it. Thanks.
Next, we have Kerry Levine, Spatial Informatics Group, talk about wildfires.
Hey, thank you all for having me and being here. I'm going to talk, transition a little bit from a data-heavy talk to more of a tools and applications talk for wildfire management as it relates to the Delta. The needs in the wildfire management realm, I really like to emphasize that we are trying to reduce the risk of harmful fires, but capitalize on opportunities for beneficial fires. So the idea is not necessarily to eliminate all fire from the landscape, but to help our landscapes come more in line with the fire regimes that they're adapted to. And to do this, we need improved tools and data for planning, prediction, and detection. I wanted to include a figure from a recent paper. The Delta Stewardship author might be in this room, but I've not met you yet. But just describing the fire effects on the hydrologic cycle upstream in the forested watersheds in the Sierra Nevada, and the effects on erosion runoff, leaching, and water quality that come along with increased wildfire extent and severity. I'm gonna focus on 3 collaborative initiatives that I've been working on that relate to wildfire risk and prediction and how they relate to climate science. I'm gonna talk first about near-term wildfire forecasting and the context of Pyrocast, a wildfire risk and behavior forecasting tool. I'm gonna talk about Planscape, which is a treatment optimization tool that can incorporate long-term climate projections into wildfire mitigation planning, and a recently developed collaborative around how to use artificial intelligence for wildfire detection and planning. So Pyrocast is a tool that we've developed that can improve fire spread and risk forecasts, and we've really focused on integrating extreme weather predictions and weather and wildfire feedbacks into this tool, as well as fuel mapping and fire physics. And like the last presentation was describing, those also relate back to climate and fuel moisture and the interactions between weather and fuels, wildfire behavior forecasting, and then climate change and fire projections. So these are the 4 main areas of research in the PyroGen's collaborative that we've integrated into this Pyrocast tool. The tool itself you can find at pyrocast.org, and the tool provides near-term fire risk and fire behavior forecasting based on current weather and 1 week out weather forecast, fuels, the interaction of fuels and weather, and it incorporates the network of wildfire detection cameras and allows you to look at fire behavior of active fires across the US. I wanted to highlight some of the tech and data innovations that have gotten incorporated into this tool in the last couple of years, in case you've seen me give this talk before. before. But we've really focused a lot on integrating fire suppression into the tool and how fire suppression moderates the fire behavior, linking it into to real-time suppression efforts. There's been a lot of updates to urban spread and structure-to-structure transmission that we're incorporating into the model. There's also an open source Python library now for fire spread simulation, but most closely related to the themes here for incorporating climate and weather. We've been working on a downscaled wind modeling and forecasting tool that can more finely predict how wind interacts with the topography and the fuels to better predict fire behavior, and also incorporating a coupled atmosphere wildland fire environment model with our colleague Janice Cohn at NCAR. The physics of this coupled wildfire atmospheric model are really complex and data intensive. So as we've been able to increase our capabilities with computing and just our compute environment, we've been able to expand on that and incorporate some of these fire feedbacks that occur within a fire system, which to date hadn't yet been incorporated in any near-term fire models. I also really wanted to highlight here our work on Planscape. Planscape is a collaborative software tool. It's a decision support tool for wildfire planning and resilience that incorporates co-benefits such as water, biodiversity, sorry, I lost my train of thought, just thinking about the water co-benefits, but we work really closely with a lot of water utilities and collaboratives around watershed management because of the tight linkage between landscape resilience to wildfire and the downstream effects on water quality and water transport. I always love to emphasize that Planscape is free, open source, open science, currently available to use for planning. I think there's a lot of opportunities for expanding the water science and the hydrology science in Planscape. So I'd love to talk more about linking into some of these other efforts and what collaborations could be useful. But the three main areas that Planscape can be used for is data analytics. So Planscape includes a suite of tools for quantifying treatment constraints and opportunities. It can be used for planning, so to generate project areas or incorporate co-benefits in planning. And then it can be used to view potential treatment outcomes, so quantify the impacts of treatments on vegetation and wildfire behavior. We have been building in climate planning into Planscape. So this tool, the Climate Foresight module in Planscape, shows how landscape conditions might change by mid-century and helps incorporate that information into current day planning. So you can plan both around current conditions and think about how future conditions incorporate into that planning, that planning effort. And I wanted to highlight one case study that we're close to wrapping up, which is we've worked with a lot of collaborative groups to help planning around multiple resilience goals, so wildfire risk reduction, biodiversity, water benefits across like large watershed landscapes. This is the example from the Upper McCallum River Watershed Authority, and that has been a really interesting case study in bringing together these multiple resilience planning goals and figuring out planning opportunities that can reflect multiple co-benefits in planning, not in addition to reducing wildfire risk. And finally, I wanted to highlight our work with the AI Collaborative Wildfires, which is a strategic initiative by Google.org, the philanthropic arm of Google, that's bringing together a really broad range of groups to figure out the best way to integrate new technologies for wildfire mitigation across hardware, software, remote sensing, and with really an eye towards better managing fires. You can see a lot of the partners across the bottom. But the roadmap for AICW is to really think about both optimizing treatments for fire prevention and reducing risk, better fire prediction, incorporating climate modeling and imagery, and then earlier detection to reduce the impacts of harmful fires when they occur, and then ultimately getting us to the point of reducing harmful fires, but promoting healthy fires and restoring fire-adapted landscapes. So I wanted to highlight the where you can find Landscape and Pyrocast, and I'm really excited to talk about how to collaborate across like my sort of wildfire silo into the water silo and bring more of that hydrologic science into these tools.
Thank you. The next talk is the final talk in the series. Before we go into the discussion session, Dan Kayan, UC San Diego. He will talk about sea level rise and flooding.
Hi, everybody. Lots of scintillating information this morning. Want to acknowledge a lot of co-authors and collaborators. In particular, in this particular snippet, Sam Icabellis has worked with me on sea level projections for the California coast and now a few locations in the Bay and sort of the outer Delta region, the second generation of those projections that we've done for the California climate assessments. State and federal sources here as far as supporting this work. So the California region and the Bay Area in particular are not unfamiliar with sea level rise. About a little over half a foot of rise in the last century. And interestingly, although global sea level rise, now seen through the lens of remote sensing technologies, has, as Swain pointed out in his talk, has probably doubled in its rate over the last 3 decades. This is the San Francisco record, which is the state's longest tide gauge record. Really hasn't budged as far as its rate of increase, and we've not observed an acceleration here along the California coast. And there's ocean circulation and atmospheric driving, including the tropical Pacific, is probably at play there. The Western Pacific, interestingly, is a hotspot of sea level rise, but the eastern boundary is not so far. The other thing to remember in our particular problem here today is the delta is subsiding, and the rate of subsidence is very uneven, but in many cases, the rate of subsidence is multiple times the rate of sea level rise. So we have this hole in the ground that constitutes the delta, that's deepening all the while sea level is rising. So that's an interesting part of this problem. And of course, neither one of those is going to change anytime soon. Okay, already covered. Global sea level rise is increasing at a rate greater now than it was 30 years ago when satellites started observing sea surface heights. And by the way, our observation systems in the nation are under assault. And it's a beautiful thing that California has its own sustenance of those kinds of things, and we have to prevail. Just desperately have to. If we look at projections of sea level under a moderate rise scenario, the exceedances over historical maximum as we look into the future increase greatly, particularly after mid-century, and they're really propelled by the global sea level rise. But by the way, there's as was mentioned, there's a broad possible set of trajectories that global sea level might take in the future. In this talk, I've kind of taken the middle road, which is being used in the current 5th California Climate Change Assessment, but it could be considerably lower, particularly in the out years through the 21st century, or it could be much higher, and a lot of that is hinging, as Swain pointed out, on the fate of the really large ice stocks in the polar latitudes. There's a state sea level rise guidance document that was updated in 2024, and that goes into the attribution of sea level rise, which there was a question about that earlier, as well as a lot of applications and so forth. So much thought and effort goes to this. So our problem in the Bay Delta, though, is that as far as water levels, there's sort of a double time scale issue. And here's another picture that my friend Mike generated that shows the really impressive portrait of heavy precipitation occurrences across the nation that can get deposited in a short amount of time, in 3 days, 16 inches or more occurrences. And of course, the Gulf Coast with the tropical storm problem stands out, but the Sierra Nevada and some of our transverse ranges in California are really special in being able to harvest these atmospheric river plumes that have been mentioned. And of course, these can generate a lot of freshwater discharge in a short amount of time. Maury Roos used to liken what happened in the Sacramento system to the much, much greater Mississippi basin. And we don't have to take too much of a backseat to this mega basin of the largest watershed in the United States in a much, much smaller watershed here, which of course is part of our problem. As we look into the future, so Laurel talked about hydrological model generation of flows, and in this case, runoff from the VIC model played through 13 different CMIP projections that were used or are being used in the 5th climate assessment in California. The sort of splatter plot there at the top is every event that exceeds the 99th percentile of flow through the 1950 through 2100 period. And you can see how the sort of paint blobs grow in size as storms. This is in mid-levels of the rim basins that feed into the Bay Delta, Lusu, working with myself and others at Scripps, generated this. But you can see the increase in intensity as the atmosphere gathers more water and occasionally deposits it. Interestingly, the annual total discharge, which is shown there in the middle panel, really doesn't change much over time. As was mentioned, we're sort of up and down. But the contribution from these Q99 daily events goes from something like 5% of the annual total in the early period to approaching a quarter by the end of the century through this ensemble of models that are played through VIC. So as was noted multiple times and so forth, we are getting much more flashy in our hydroclimate here and, constituting both, well, this is important because the atmosphere can't take as much from these flashier events, but on the other hand, we have to manage it when it happens. So now the water level problem is actually in the short range, these bursts that we see that occur episodically are winter storm driven largely in California. We don't have a hurricane problem here in the Bay Area, but we do have a winter storm problem, and occasionally we get really large winter storms. So the largest sea level still that has been recorded at the San Francisco gauge is 27 January 1983, notorious El Nino year, of course. But during that period of late January, we had king tides, and we had one of these very large storms. That storm took out virtually all of the vulnerable structures along the California coast, including the Scripps Pier, right down the shoreline. Waves were washing through the marine room, restaurant, it sits perched on the bluff above the ocean. And you can see this is the 500 or the 700 millibar geopotential height surface, and you can see the huge fetch of strong winds that issued from that storm, and at the same time rose sea level, but at the same time generated quite a lot of precipitation. And by the way, this wasn't just a one-day event, it was a sequence. It may not be the 1862 siege that was noted earlier, but this is the fingerprint of what causes really high sea levels. Now, the other really important thing, though, is that when you canvass the sea levels from the astronomical tides and the sea level residual, the anomaly that occurred in that storm, it could have been worse. So that storm resulted in sea levels that were about 1.7 meters above the mean sea level at the time. But if we just play a game and ask the question, if we superimpose the highest tide that we could have achieved and the highest residual that we could have achieved, we can create a sea level that's about 2.3 meters. So another half a meter above the highest sea level that's been recorded at San Francisco. Now, that's very much a luck of the draw issue because, you know, these processes are to some extent random, and we've dodged a lot of bullets in the meantime since 1983. Really large El Nino in 1997, 98, 2015, 2016. But even though we had big storms, to some extent, we missed king tides and so forth. So, you know, we're playing a game here of trying to avoid these coincidences. The extended range week 2 problem that Ben mentioned in his talk, I think is really important for a lot of these shorter period hazards, because the longer window that we have to look forward at these kinds of things, the better off we're going to be as far as preparation. And we know what we have to prepare for. So what we've done here is we've looked in, again, through the lens of these sea level projections, coupled with high, in this case, high precipitation that I've accumulated over 7 days. And I've looked at the confluence there, the histogram-like bars in this time series plot shows the coincidence of very high sea levels and very high precipitation events. And you can see over time this, this increase that occurs. Again, it's propelled largely by the rate of global sea level rise. But not only, it turns out that there's a dynamic effect where storms along the western margin are actually getting dynamically a little stronger. And so that couples into this too, as well as the fact that, of course, storms are getting richer from the thermodynamic effect of just more moisture. So all of those things are coming together. I think there's a number of messages, probably taking too much time, and maybe we get into this with the discussion. So, thanks.
Yeah, we're a little behind, but we should have enough time for Q&A. Maybe we should ask the panelists to come here to these chairs. All right, so I don't know about you, from the talk this morning, my head is spinning. You know, so many things to think about when we look at future hazards and what we are trying to do in terms of planning. So we'll open up for Q&A for any of the speakers, and I would ask the speakers, you don't have to limit your expertise to the topic you talked about. So, and I think we should get some questions from the online as well. We had like 70 some people online earlier, but let's go to the audience here, and I think there's a question in the back. Oh, sorry, go ahead. You decide who to go to, Jonathan.
Okay, hi. So I think this is a question directed to Alan. So one of your last bullets was the unintended consequences for FIRO and flood-mar. I just wanted to reopen up more time for that and like talk about those conflicts and resolutions for that. Thank you.
Yeah, thanks for the question. Where do I go with this? I just think that oftentimes, and I'm totally for flood-mar and FIRO as two good science-based approaches that could lead to more volumes of water being stored in the ground and not quote unquote wasted, right? Especially as snow is continuing to be lost and coming out in a flashier melt. So I just think that there needs to be more science-based exploration, maybe through these storyline approaches I mentioned, of unintended consequences of having maybe a similar 1997 event, but maybe with a synthetic add-on of a sequential AR event that that sequencing of what we might expect in the future warmer world. I just think we need to explore that a little bit more and look at these like local precipitation bursts that might occur over a farm region or in the headwaters of the Sierra, that if you're trying to convey water, there's the amount of time it takes to convey that water. You get it to the field, then you try to percolate it down into the groundwater. That takes time. And if these series of storms come a lot more in succession and produce bursts of rainfall, I think that's underexplored. So hopefully I answer your question, and also not just have scientists doing it, right? But be informed by the practitioners or land manager, maybe even city officials, city planners, depending on where you're looking at.
And something that this makes me think about as someone who grew up in Davis, and we have lots of orchards, lots of fallow lands, lots of opportunities to do flood-mar and FIRO, but understanding putting that water on somebody's land may mean that their orchards are flooded. That may have implications for their operations, even in the non-growing season, as well as it may damage their crops in the future, or it may transport and deposit pollutants or sediment into that area. And those kinds of things, I think, can be dealt with through a community-based approach of incorporating folks to get little test bed areas, sampling that to show what we can do and what we can't do. And I think that's a good way to build that trust in the community. And then maybe more on the science side, better hydrogeological characterization of good locations to do this and other locations where it may be not as good. And so I think we have lots of land to work with and lots of opportunities for that, but there's still many questions. But I think those really, I like to view the challenges as opportunities and ways to bring science to the community, incorporate the community in that science and decision-making process, and then really highlight those kinds of things.
I think unless there's any other feedback from the panel, go ahead, Steve.
Yeah, thank you. Steve Culberson, the Delta Stewardship Council, and this will be an unfair question, but I hope you won't duck it. I'm increasingly impressed with the technical capabilities that we have in this community, and that has emerged over a period of decades that we've all been watching. And so nothing against the conversations that you're all having now amongst you and your colleagues. But I have to say that on the policy side and for the realities that we're facing in terms of managing water resources in California in particular, I don't find much of what you're talking about actually informing the discussions at the basis level, like who's getting what water and why, and who's planning on how much water we have available and when. So would any of you like to take a shot at helping me understand how this incredibly convincing, to me, technical information actually works its way to a limited resource allocation strategy or responses to that kind of thing? Anyway, I understand if there's not an answer to this, but I think it's something that we in the technical community should be taking on full bore. I don't see any shortcomings with the technical stuff that's being discussed here today. What I see is a shortcoming of transferring that information to people who actually are making the decisions and investing resources. So, okay, so fair enough. If that's the question, come back for the next panel, that's fine.
Yeah. Yeah. There is a question for the panel we'll get into a little bit later. What are the biggest gaps and uncertainties of our scientific understanding? I'm going to ask that question from the panel. Go ahead, Dan.
Hi, Steve. Well, I think a good disaster is actually an important elixir for politics, which I think, a lot of what you're concerned about is sort of human behavior and the difficulty in making decisions in a collective way. But, so Superstorm Sandy and the changes that it had brought about, I think is a good lesson. And unfortunately, collectively, we don't do a good job of acting in advance of, hazards. It really takes one to, get our act together. So, and, that can go along, lots of different ways to think about that. But that would be my guess, is that I think we need to have in our back pocket plans so that when one of these events comes along, we can actually make strides.
Anybody else in the panel to respond to Steve's comment or question? Go ahead.
I have a minor point that I think you need to get the incentive structures aligned between academic researchers, because a lot of times our metrics of success, especially the Department of Energy, is first author publications, that'd be novel research, but there's not really metrics of success of being a boundary spanner in translating science or intercomparing science or finding those uncertainties and gaps within that intercomparison necessarily. So I think I don't work for the PPIC or things like that, but I find it as a good boundary spanner that takes the best available science, translates that hopefully to policy relevance, and I think more engagement with those sorts of organizations could be really valuable, and realigning incentive structures at academic institutions that don't just value first author publication, but a broader sense of success.
Go ahead. Yeah, go ahead.
I'm Roman Mendley. I'm with the Department of Water Resources. So first of all, thank you. It's always nice to see all you guys talking about climate change. I always learn something about it. First prompt is FIOMAR will have a report out in November about finding and raising our climate change analysis in the department. So I'm very excited to announce that. And the second one is a question related to thermodynamic and dynamic changes related to climate change. So it sounds like, in general, we have a good sense of where we're heading with thermodynamic through Celsius Capron and super Celsius Capron on the extreme drought and extreme wetness. I was wondering if you have a sense about how dynamic changes were a little bit more complex to understand, or pull apart from natural variability of climate is going to affect the hydrological cycle. Do you have a sense of where we're heading in this space? Because I think that's one of the challenge, again, good sense of thermodynamic, we can increase extreme, but on the dynamic space, it's a little bit more murky in my head. Thanks.
Yeah, so I think we have a very good understanding of the thermodynamic side of things, as you indicated. I think on the dynamic side, I don't really have any particular trust in climate model projections about dynamic change. Many of them have, for instance, the intertropical convergence zone moving farther north, others have it not, or have it moving farther south, and there's going to be variations in the North Pacific high, of course, which will affect precipitation in California on a year-to-year basis. So the dynamics is hard to tease out. I would say, however, that there are a lot of more localized regional dynamical effects that deserve further investigation. For instance, we know actually that there is going to be enhanced drying on the windward side of the Sierra Nevadas. That is the side that's most important to us here in California, because of the increases in basically where water is located in the atmosphere. Because of that warming effect that we have through the thermodynamics, you actually get an expansion of the layers of the atmosphere, and that pushes more water higher up in the atmosphere and thus makes it easier for that water to pass over the Sierra Nevadas. So even if you have the kind of enhancement in total water vapor content that we've seen in some of the earlier results today, we're not going to get all that much payback necessarily from that. And there's a lot of open research right now on exactly how much that will affect the amount of water resource availability that we have. In addition to that, there's a lot of very good work going on kind of coastal effects and how those increases in the temperature gradient between over land and over the ocean will also influence some of the weather patterns that we experience here in California. And I would say those local effects are more important from the dynamical perspective than where we see kind of the larger patterns shifting, because there's so much uncertainty when it comes to those larger patterns.
Yeah, go ahead. I think we need a, oh, go ahead.
I guess I have.
Okay, go ahead, Bob, first.
Bob Nyman, University of Washington. First of all, thanks for the presentations. They were all informative and really interesting to me. I have a simple question, unlike Steve's question. I think mine is pretty straightforward. And I'm especially interested in the atmospheric rivers. And I was wondering, are there individuals or groups that are investigating the environmental consequences of having more powerful and numerous atmospheric rivers going forward? I'm thinking specifically about things like bed loads. I would think that bed loads are increased dramatically, as well as flux of carbon to the delta and so forth. So anyway, I'm just curious as to who might be looking at the environmental consequences of these changes.
Yeah, I think, and this is, I think we're supposed to say our name. This is Ben Hatchett. I think some of the work, like I shared Erica Cirola Woodburn's work and some of the other work that the Berkeley lab is doing, helping to translate these storms and their hydrologic effects into geomorphic, fluvial geomorphic effects or other ecosystem impacts are super important. And I think there's a ton of room to expand that. I'm not personally familiar with a bunch of examples I could give you off the top of my head. Perhaps others here are. Mike, absolutely.
Hello? Okay, good. A name, Christina Bono at Desert Research Institute, just this past spring, I suppose, got one of those NSF early-ish career awards specifically to take the FERO stuff that we've been hearing occasionally about and bring in a greater ecosystem impacts and benefits element to that. And, yes, and our FERO in California, which is where she'll be working, is AR, really strongly AR biased or based. So, but she's just spinning up if you've got ideas. Yeah. Thank you, Mike. Dan, I think your turn, and then I'll go to you, Steve.
Yes, my question was getting back to the topic of infrastructure vulnerability, which has come up a number of times, and I know that'll be a topic for tomorrow, but what I guess for Alan, would this storyline approach be a way to identify which of the aging infrastructure components that impact the delta should be worked on right now to prepare for what might happen in 10 years or 20 years? Because we are at this point where there's been not only aging infrastructure, but infrastructure coming up for relicensure and all that. So that's one of my questions. Thanks.
Yeah, that's a great question. I would be really excited to work more collaboratively with like the U.S. Army Corps or people at DWR on modeling of the built infrastructure and the management assumptions within it and coupling it with some of our storyline events. But I hesitate to say which storyline event should be used, and that I might like have a conversation with them first. But I think that's a great idea of like thinking about storylines that, like a handful of them, and then seeing where the vulnerabilities really arise throughout the infrastructure, and like if there's any hotspots or commonalities of issues that might arise, and maybe that could help planning. It's a great idea.
A bit of a tangential comment based on what Alan basically indicated, but I think that there's a big gap in terms of our scientific understanding of what is the state space of possible scenarios. We obviously have what we've experienced historically, but we've also missed a lot of potentially very devastating scenarios. And so we don't know how to effectively tease down that state space of possible scenarios to a few scenarios that effectively allow us to explore all possible high impact consequences and their corresponding probabilities.
Yeah, go ahead. Then I'll go to the questions for the panel, the same question for every panelist.
Stefan Tolka, Cal Poly. I'm wondering, in your opinion, what are the things we're not thinking of? What are the blind spots that we have not heard today? One thing that comes to mind is water temperature, but I could probably think of other things. But I'm just curious what you think, as a community, people are not thinking about.
Anybody wants to respond?
This may be, it's not a local thing, but in 2021, we had a fire in Boulder County in Colorado that was so far outside of the annual fire season. It was actually December 30th. And what we didn't recognize at the time was that we'd had a super wet spring, followed by an extraordinarily dry summer and fall and early winter, and then a windstorm. I guess my point is, it seems so obvious in retrospect, but we were not prepared for what happened. And what happened was we lost 1,000 homes, in whole towns were destroyed. So these sort of cascading effects are very difficult. I mean, I guess this gets to the question we just asked. These cascading effects are very difficult to decompose. And we immediately put forward a grant to look for this sort of whipsaw of behavior, when the spigot just gets turned off, and the effects on fire, and it was rejected. But I think that's one example, this sort of hydrologic whipsaw. I guess that's not the phrase. Somebody can remind me. Somebody talked about it. You talked about
Yeah,
it.
so I'm sorry.
Whiplash, that's it, yes.
Edmund, do you have somebody else, or do you want me to?
We have two more in person and one online, but I want to manage time because I know you have two questions as well.
Yeah, I have. I will only
person.
ask one question. Can we go to the online one maybe first?
Okay.
We never got a chance, and then we'll go to the in-person one.
Just while we're going to the online one, an additional thing that we're not really thinking of that much is sudden transitions, particularly in the ecosystem. It's very clear that around mid-century, the forests of the Sierra Nevada will transition out of their natural climate regime and into a climate regime more conducive with the shrublands and brushlands that we see in Southern California. And those forests are likely to collapse very suddenly, either via a widespread wildfire event, bark beetle infestation, or some other cataclysmic event that will cause a sudden shift in that climatic regime. And I don't think that we're studying enough what the consequences of that will be after we undergo that tipping point.
Why don't we get to the online question and then any other question in person, and then at least I want to ask at least one of the two questions I have for the panel. So go ahead.
All right, so there's two online questions. I'll read the first one first. This one is from Martine Schmidt-Pullman. Adding to the comment and Alan and Paul's responses, I'd be curious to know how much cross-agency infrastructure coordination is done in the Delta. And for our panelists, please be sure to state your name before providing your response. Thank you.
It was directed at me. So can you repeat the question? It was cross-agency collaboration?
Yeah, I'll be curious to know how much cross-agency infrastructure coordination is done in the Delta.
That's a very precise question. I don't know if I'm
Yeah.
fit to answer that.
That could be like either afternoon or tomorrow's session, right? Can that be?
I'd love to know, though.
Yeah, so stay tuned for tomorrow.
Yeah.
The next one is from Deirdre Desjardins. 2 major federally funded papers on northward shifts of atmospheric rivers came out in October 2024. Lee et al., UC Santa Barbara, funded by NOAA's Climate Program Office, and March 2025, Dong et al., UCAR, and NOAA GFDL. The US government has severely curtailed funding for NOAA climate research. How do we get people to incorporate these results into climate adaptation efforts before it is lost?
Anybody on the panel?
Maybe to spin that question back to an earlier question about blind spots or what we're not thinking about. And I don't necessarily know it's a blind spot, but I'm really worried about the brain drain that's currently going on, where there's not as many academic positions for bright superstars that are coming up through the scientific field. And that'll leave us even more vulnerable to these sorts of questions we're asking right now. And unfortunately, the other thing is that with our monitoring networks, a lot of them are potentially at risk of being lost too, or some of it. And so we need to find alternate pathways of getting funding to support those future stars in science and maintain the monitoring networks that we do have to continue to think about the trends.
Yeah. Well,
I guess I would say, this is Ben Hatchett. I'd also add to that the need for the scientists, us, everyone in this room, to do our best to push for getting these scientific findings into assessments. And maybe it takes, we all have too much work to do, but maybe it takes extra time to say, you know what, I'm going to volunteer to be on the Bay Area chapter of the California Climate Change Assessment because I think this is important and it's not being funded anymore. I previously was on the 5th, or maybe it would have been the 6th National Climate Assessment. That is no longer happening, but we're going to have to take some of our own time, and that onus falls on us a bit to help bring the research into the real world, into the practitioner space, and that, yeah, it takes time, but I think that's what we're going to have to do until we can sort out funding opportunities from other places, and that's perhaps also getting at the point I was making earlier on involving the community, getting the community excited, showing them why their hard-earned tax dollars matter for this work, and bringing that work and that interest so that they push that up the chain through their county supervisors, through their representatives, and be able to kind of flip things around, but really highlight stuff from the ground up by involving them, and then also kind of from our end, pushing out into places that we're maybe not as comfortable working in necessarily. And part of that also will come from what Alan mentioned with the changing of the incentivization structure. It's not just, you work with communities, you might not get a bunch of papers that year, but you're gonna make a ton of friends, and it'll, you'll leave the place in a better area than it started. Not that nothing feels better than that.
Yeah. Let me go to the last question. Peter, do you have a question? Otherwise, we'll go to the common question for everybody.
Yeah, Obey, it looks like we have 4 more in person. I believe Peter, Rachel, Anna, and Lisa.
Okay.
If you want to take a break and answer and do some of the panelist questions, I think we can do that as well.
No, I think we'll go to the panel question last. We'll go through this in person. Yeah. Good. What's that? Okay. Okay, let's go to Peter first. He was, but I think the panelists wanted to hear from the board members as well. So if you have a question, feel free to ask or comment. Go ahead, Peter.
Well, thank you, and I'll try and keep this quick. Peter Goodwin from UMCS. And first of all, I think it was really inspiring just to hear the richness of research which is going on this topic this morning. So thank you for that. I had a very specific question. I remember a few years ago being here and seeing a presentation with a lot of qualifiers by Roger Bales and his group that was showing that if we were to manage and return our forests to a more natural situation, the benefits associated with that, reducing wildfire risk, but also the potential for increasing stream flows that could then be used with the cost of water to pay for management. And there were several other people around the world finding similar conclusions. I just wondered where the state of that was. Did those very preliminary findings pan out? Is there a significant increase in water flows as well as wildfire reduction?
Yeah, so I've been working with Roger. This might have been a more pertinent topic for this presentation, but we have been working for the last several years with the Wildfire and Forest Resilience Task Force in California, modeling 6 different scenarios of treatment effort and allocation across the state of California and the effects on vegetation and wildfire behavior. And I did the vegetation and fire modeling, and Roger and his postdoc have taken those results and are now calculating the water benefits directly for those 6 statewide scenarios for 20 years of forest and wildland fire resilience treatments. It's also getting worked into an economic model of the cost of those treatments based on the location, the treatment type, and the intensity. That's being worked on by an economist at CAL FIRE. So all of that's getting integrated into the update to the action plan, which the task force is releasing later this fall. So that should all be available shortly. Yeah. But it's been a long effort. And I know Roger's working on a lot of other stuff in that realm as well. But in terms of like long-term statewide scenario modeling, that'll be available in the next few months.
Let's get to the questions from the board members. We may have to go to lunch before I get to the second question, but I will mention the second question. We can talk one-on-one and get the response. Lisa, were you one of them? Okay. How about Tanya? Do you have? What's that? Okay. Anybody? Yeah, Anna.
I have a question for everyone, which I hope is quick. If you think back just over the last 5 or 10 years for the topics that you addressed in each of your presentations and thinking about the Delta specifically, could you each just take maybe 30 seconds to name one thing that we know now or we understand better now relative to just 5 or 10 years ago? So where do you see the biggest jump in our scientific understanding?
I'll start from the fire perspective, and I would say it's the urgency is the main difference now from 10 years ago, and just understanding that solutions don't have to be perfect, but they have to be fast.
Well, that's a thought-provoking question. I think we know a lot more about large atmospheric events and the importance of the rarest events in driving the overall longer-term status of our hydroclimate. So Mike Dettinger there is one of the savants in that area, and there's been a lot of other work, but I think that area in climate work is kind of bridging the shorter term and the longer term activity, I think has really advanced.
Yeah, and I think I'd go back to the improvement in skill at the sub-seasonal, so those week 2, week 3 forecasting of extreme events or the lack of extreme events. It's just as important to understand that we're going to go into a 2-3 week dry spell as it is that we're going to see 7 landfalling atmospheric rivers, because those are the two drivers. And that's, I think, extending, Anna, your question to even longer timescales of this better understanding that the mean only means so much, but it's really the variability that drives the system and perturbs the system. And so being able to forecast those perturbations more skillfully at longer lead times, at higher resolution, to where we can really pick down the specific watersheds that may be responding has been probably the most remarkable thing I can see happening in the last few years.
Yeah, this was a great question. I think from a snowpack perspective, from a climate projections perspective, I think the time of emergence of when low to no snow conditions might arise in the Sierra or different mountains has been more constrained. But I still think that we need maybe a little bit more work on that spatial structure of how that change looks.
I don't really have a Delta perspective. I don't really work in the Delta specifically. But our lab has been working a lot on the concept of flash droughts. This is not something I've really talked about a lot, just mentioned it once or twice. But the recognition that flash droughts, recognizing flash droughts and understanding that they are the events that happen within our decision cycle. They're too fast for our decision cycle. We have a hard time keeping up with them. How do we then predict them? And we're starting to uncover that. And one of our tools is to decompose the demand side, which I did talk about a little bit. And the second thing is the connection between these droughts, and all droughts, in fact, and wildfire. I think our lab is putting a lot of effort into that particularly.
From the climate model perspective, I would say that we have a much better idea now of where climate models are trustworthy and where they probably need a little bit more work. And we've definitely improved on the climate modeling side, representation of regional to local phenomenon. I would also add that I think over the past 10 years, because of how much interest there is in climate change and its implications, we have a much better understanding of how climate change from the natural system perspective can then filter through the human system and the potential consequences of those cascades. I think that there's a lot more work to be done when it comes to understanding that interconnected natural human system and some of the implications of a disturbance to those systems. But I think that we've done we've made substantial progress in that front.
Yeah. All right. Let's. I'm going to put my board member hat and make a comment, and then maybe we can wrap this up so everybody can have lunch on time. When I said my head was spinning, I was not joking, because I heard about the step change, I heard about whiplash, and I heard about increasing probability of black swan type events and a whole bunch of other seasonal changes. So from a board point of view, we want to know, are the practices currently being used for modeling or simulations, are those adequate to reflect those scientific findings? So the question here is kind of second part of Anna's question. We won't go through that now, but think about it, and maybe we can talk to one-on-one. What are the biggest gaps and uncertainties in our scientific understanding? If you had to pick one or two of them, what are they? And considering that they matter in terms of planning for large-scale water resources systems like this. And I think that's the question. So anyway, with that, we're actually only 3 minutes behind our schedule for lunch. And we will get back, think about my comment or question, and we can talk one-on-one. So fortunately, Dr. Lisa Wenger will be facilitating the second half of this day. And we will gather back at 1:40 p.m.